Welcome to the story of the first human mission to Alpha Centauri. Part 1: The Dream Beyond Our Stars. From the earliest days of human civilization, we have gazed upward at the night sky, wondering what might exist beyond our reach. For millennia, the stars remained just that, distant points of light, forever unattainable. Yet the human drive to explore has never diminished. With each technological leap, we pushed farther. Across oceans, into the skies, and eventually beyond our atmosphere to the moon and later to neighboring planets. But the stars remained elusive, separated from us by the vast emptiness of interstellar space. In 2025, our closest stellar neighbor, Alpha Centauri, stood 4.37 light-years away. Such a modest number belied the true scale of the distance, approximately 25 trillion miles. For perspective, if Earth were the size of a marble, Alpha Centauri would be positioned roughly 50 miles away. Our fastest spacecraft at that time would have required tens of thousands of years to make the journey. The dream of reaching another star system seemed destined to remain exactly that, a dream. Yet the scientific community never stopped looking toward Alpha Centauri. This triple star system represented our most promising first target for interstellar exploration. Alpha Centauri A and B formed a binary pair of stars, orbiting each other in a cosmic dance that takes 80 years to complete. Alpha Centauri A bore a striking resemblance to our own Sun, a G-type yellow dwarf star with a similar mass and brightness. Its companion, Alpha Centauri B, was slightly smaller and cooler. The third member of this system, Proxima Centauri, orbited far from this binary pair, a small, dim red dwarf that, despite its faintness, held the distinction of being the individual star closest to our solar system. The early 2020s brought an intensification of interest in this nearby system, with continued observations of Proxima b, an Earth-sized exoplanet discovered in 2016, orbiting within Proxima Centauri's habitable zone. The potential for this world to harbor liquid water on its surface captivated the public imagination. By 2028, further observations had identified additional planetary candidates throughout the Alpha Centauri system, including possible worlds around the Sun-like Alpha Centauri A, worlds that might offer even more Earth-like conditions than those orbiting the volatile red dwarf Proxima Centauri. The discovery in 2030 of complex organic molecules in the atmosphere of one of these worlds set off a new wave of scientific excitement. While not confirmation of extraterrestrial life, it suggested the basic chemical precursors for life might exist beyond our solar system. The question of whether we were alone in the universe suddenly seemed answerable, if only we could reach Alpha Centauri. But the limitations of early 21st century propulsion systems presented an insurmountable barrier. Chemical rockets, which had carried humans to the moon and robotic explorers throughout our solar system, operated on principles fundamentally unsuited for interstellar journeys. The rocket equation, first derived by Konstantin Tsiolkovsky in the early 20th century, established the mathematical relationship between a rocket's final velocity, its exhaust velocity, and the ratio of its initial to final mass. Put simply, to go faster, a rocket needed to carry more fuel, which made it heavier, which in turn required even more fuel. This exponential relationship created a practical ceiling on the velocities achievable by chemical propulsion. The fastest spacecraft as of 2025, NASA's Parker Solar Probe, reached speeds of around 430,000 miles per hour as it swung close to the Sun. Impressive as this was, it represented less than 0.1% of the speed of light. At such velocities, a journey to Alpha Centauri would take thousands of years. Even with theoretical improvements, chemical rockets appeared fundamentally incapable of delivering the required performance for interstellar travel within a human lifetime. Alternative propulsion concepts existed, but remained in their infancy. Ion drives, which use electric fields to accelerate charged particles, offered much higher exhaust velocities than chemical rockets, but their extremely low thrust meant they could not produce the rapid acceleration needed for interstellar missions. Solar sails, which harness the pressure of sunlight to generate propulsion, suffered similar limitations, and their effectiveness diminished rapidly as spacecraft moved away from the sun. The year 2031 marked a turning point in humanity's interstellar aspirations. The Breakthrough Starshot initiative, originally announced in 2016, received a massive funding injection from a consortium of global technology magnates. The goal seemed simultaneously modest and audacious: to send a fleet of gram-sized Starship probes to Alpha Centauri. These tiny spacecraft would be propelled by a ground-based laser array reflecting off ultralight sails, potentially reaching 20% of light speed and arriving at Alpha Centauri within a human lifetime. While the earliest Starshot prototypes proved the basic concept feasible, they also highlighted the enormous technical challenges. The first full-scale test, conducted in 2035, managed to accelerate a prototype sail to merely 0.01% of the intended velocity before the delicate structure disintegrated under the intense laser pressure. The project's engineers returned to their design tables, but the public imagination had been captured. For the first time, reaching the stars seemed to be transitioning from science fiction to nascent engineering project. The following years saw the establishment of dedicated research institutes focused on the interstellar travel problem. The Tau Zero Foundation, expanded in 2038 with substantial international funding, brought together physicists, engineers, and materials scientists specifically to tackle the challenges of interstellar propulsion. The European Space Agency founded its Interstellar Flight Research Center in 2040, with similar institutions appearing in China, India, and Japan shortly thereafter. These research centers focused not only on the Starshot concept, but began exploring a broader range of propulsion technologies. Fusion propulsion, which had long been theorized as a viable approach for interstellar travel, received renewed attention. By harnessing the same energy source that powers the stars themselves, the fusion of light atomic nuclei into heavier ones, fusion rockets promised exhaust velocities orders of magnitude higher than chemical propulsion, potentially enabling travel at a significant fraction of light speed. In 2042, a breakthrough occurred at the International Fusion Facility when researchers maintained a stable fusion reaction for over 100 hours, far longer than previous attempts. While still far from a practical propulsion system, this demonstration proved that sustained fusion was achievable. The prospect of using deuterium-tritium or deuterium-helium-3 reactions to power spacecraft began to seem less like science fiction and more like a future engineering challenge. Computer modeling played a critical role in these developments. As quantum computing reached practical maturity in the 2040s, scientists gained the ability to simulate interstellar missions with unprecedented detail. These simulations revealed challenges that had previously been overlooked or underestimated. One such challenge was the interstellar medium itself. While often thought of as empty, the space between stars contains diffuse gas, dust, and high-energy particles. At the velocities required for interstellar travel, a significant fraction of light speed, impacts with even tiny particles would release tremendous energy. Simulations showed that a grain of dust striking a spacecraft traveling at 20% of light speed would hit with the force of a small explosion. New shielding concepts became necessary, from layered sacrificial barriers to magnetic fields designed to deflect charged particles. Radiation presented another major hurdle. Beyond the protective cocoon of Earth's magnetosphere, space is pervaded by intense radiation from both solar and galactic sources. High-energy cosmic rays can penetrate conventional shielding materials, damaging both electronic systems and living tissue. Long-duration space missions would expose crews to radiation doses far exceeding safe limits unless effective countermeasures could be developed. Early experiments with passive radiation shielding materials showed promise. Hydrogen-rich compounds, which effectively absorbed cosmic radiation, became a focus of research. Water, already necessary for life support, emerged as a potential dual-purpose resource, both sustaining a crew and helping protect them from radiation. Computational models suggested that a water layer just 5 meters thick could reduce radiation exposure to acceptable levels for multi-year missions. Active shielding approaches also progressed during this period. The magnetic radiation shield prototype, tested on the Lunar Gateway space station in 2045, demonstrated that superconducting magnets could create a protective field around a spacecraft, deflecting charged radiation particles. While the power requirements remained prohibitive for full-scale implementation, the proof of concept represented a significant step forward. By the mid-2040s, international cooperation became essential to progress. The scale of the technical challenges and their potential solutions exceeded what any single nation could address alone. The Interstellar Coordination Treaty of 2046 established a framework for global collaboration, pooling resources and expertise while ensuring that the benefits of interstellar exploration would be shared by all humanity. Under this treaty, the Alpha Centauri mission directorate formed, bringing together scientists and engineers from dozens of countries. Their mandate was clear: develop the technologies necessary to send humans to Alpha Centauri within a century. The deadline seemed arbitrary, why not sooner or later? But it provided a concrete timeframe that focused efforts and resources. The first tangible product of this collaboration came in 2048 with the successful test of an experimental fusion drive. Conducted in Earth orbit with remote operation for safety, the test produced a sustained thrust using deuterium fuel for nearly 30 minutes before an instability in the magnetic confinement system forced a shutdown. While modest in performance, the drive generated only enough thrust to change the test vehicle's velocity by a few meters per second. It represented the first working prototype of a propulsion system that could theoretically reach Alpha Centauri within a human lifetime. The year 2050 marked the end of what historians would later call the conceptual era of interstellar travel. The fundamental scientific questions had been addressed, at least in theory. Yes, interstellar travel was possible within the known laws of physics. Yes, there existed plausible technological pathways to achieve it. And yes, there were compelling scientific reasons to undertake such a journey, from the search for extraterrestrial life to expanding humanity's understanding of the universe. As the mid-21st century arrived, the focus shifted from theoretical questions to practical engineering challenges. The dream of reaching Alpha Centauri had evolved from pure fantasy to a distant but achievable goal. The stars no longer seemed entirely out of reach. The path ahead remained long and uncertain, but for the first time in human history, there was a path. The question was no longer if humans would travel to another star, but when. The greatest journey in human history had begun, not in space, but in the laboratories, research centers, and collaborative projects across Earth. Our species stood at the threshold of becoming truly interstellar, ready to take the first concrete steps toward the stars that had beckoned us since the dawn of consciousness. But no one anticipated the scale of the challenges still to come, nor the ingenuity that would be required to overcome them. The dream of Alpha Centauri had been established. Now began the long, difficult work of making that dream a reality. Part 2: Building the Foundation. The middle decades of the 21st century marked humanity's transition from merely dreaming about interstellar travel to actively creating the technologies that would make it possible. The conceptual groundwork laid in the previous quarter century now needed to be transformed into functioning systems capable of propelling humans across the vast gulf to Alpha Centauri. This period would test not only our scientific and engineering capabilities, but also our collective will to pursue a goal whose completion might lie beyond the lifetimes of those who initiated it. The most fundamental challenge remained propulsion. Chemical rockets had taken humans to the moon and robotic probes throughout the solar system, but their inherent limitations made them utterly impractical for interstellar journeys. The year 2052 brought what many consider the pivotal breakthrough in fusion containment technology. At the International Fusion Research Facility in Japan, scientists achieved stable plasma confinement for over 200 hours using a modified tokamak design with superconducting magnets cooled to near absolute zero. This breakthrough came from an unexpected direction: the integration of artificial intelligence into plasma physics research. Quantum neural networks, running on the latest generation of quantum computers, analyzed countless simulations of plasma behavior and identified containment configurations that human researchers had overlooked. The mastic configuration, named after the AI system that discovered it, created a more stable magnetic bottle by dynamically adjusting field strengths in response to plasma fluctuations at microsecond intervals. With this achievement, fusion energy for terrestrial power generation became commercially viable within the decade. More importantly for interstellar aspirations, a pathway to fusion propulsion emerged. The Alpha Centauri mission directorate immediately redirected resources toward adapting the mastic configuration for spacecraft propulsion. Their efforts culminated in 2056 with the orbital test of the Rufus 1, the first functioning fusion rocket prototype. Conducted in high Earth orbit for safety reasons, the Rufus 1 test exceeded all expectations. Using deuterium-tritium fuel, the engine produced a sustained specific impulse of 200,000 seconds, more than 40 times greater than the best chemical rockets. The exhaust velocity approached 1% of light speed. While still insufficient for practical interstellar travel, it represented a quantum leap in propulsion capability. Following successful tests, engineers immediately began developing the more advanced Rufus 2, designed to use the more energetic deuterium-helium-3 reaction. As fusion propulsion advanced, the competing technology of laser-pushed light sails continued its own development path. The breakthrough Starshot initiative, after decades of materials research, successfully demonstrated a graphene composite sail capable of withstanding the intense laser pressures needed for interstellar velocities. In 2058, they conducted their most ambitious test. A full-scale prototype sail was accelerated to 0.1% of light speed using a 50-gigawatt laser array in lunar orbit. The sail survived intact, validating the fundamental concept. This achievement sparked debate within the scientific community about which propulsion approach offered the most promising path to Alpha Centauri. Laser sail advocates pointed to the simplicity of their approach: no need to carry propellant, potentially higher ultimate velocities. Fusion proponents countered with their system's ability to decelerate at the destination and the potential for human transport rather than merely sending miniaturized probes. The Alpha Centauri mission directorate ultimately chose to pursue both technologies in parallel. This decision proved prescient when, in 2062, researchers at the European Space Agency developed a hybrid propulsion concept that integrated elements of both approaches. The Bifrost system used laser arrays to heat and contain fusion plasma externally to the spacecraft, essentially creating a laser-supported fusion reaction that could achieve both high thrust and unprecedented specific impulse. Computer simulations suggested the Bifrost system could potentially accelerate a substantial spacecraft to 10% of light speed, enabling a journey to Alpha Centauri in approximately 44 years. While still theoretical, this hybrid approach offered the most promising path forward for a human mission to another star. Engineering development began immediately, though full implementation would require infrastructure far beyond what existed at the time. The infrastructure requirements for constructing, launching, and supporting interstellar spacecraft represented a challenge nearly as daunting as propulsion itself. Earth's existing space facilities, the aging International Space Station, and various national outposts in low Earth orbit were wholly inadequate for assembling vehicles of the necessary scale. Recognizing this limitation, in 2055, the Global Centauri Initiative began construction of the first dedicated orbital manufacturing facility in Earth-Moon L1, a gravitationally stable point between Earth and the Moon. The Orbital Assembly Platform, or OAP, took 7 years to complete. Built using materials launched from Earth and increasingly from the Moon as lunar industry developed, the OAP spanned over 1 kilometer in length when finished in 2062. Its vast hangars, precision fabrication facilities, and radiation-shielded habitation modules provided the first environment where truly large-scale spacecraft could be assembled. The facility's location also offered ready access to both terrestrial and lunar resources, while minimizing the energy required for launches from either body. Resource acquisition proved critical to these infrastructure developments. The mass requirements for interstellar spacecraft made launching all materials from Earth's deep gravity economically prohibitive. The solution emerged in the form of asteroid mining, which progressed from experimental demonstrations to industrial-scale operations during this period. The Asteroid Resource Corporation, formed in 2059 through an international public-private partnership, deployed its first fleet of autonomous mining vessels to near-Earth asteroids. These operations initially focused on water-rich carbonaceous asteroids, extracting both water, which could be electrolyzed into hydrogen and oxygen for fuel, and rare metals valuable for spacecraft construction. By 2065, a steady stream of resources began flowing from near-Earth space to the OAP, dramatically reducing the cost of space construction. These developments coincided with breakthroughs in closed-loop life support systems, essential for any mission lasting decades. Early space stations had relied on regular resupply from Earth, with limited recycling capabilities. True interstellar travel would require nearly perfect resource recycling, with minimal loss over decades of operation. In 2057, The Biosphere 3 project was established in the Arizona desert as a testbed for closed ecological systems. Unlike its predecessors, Biosphere 3 incorporated the latest advances in synthetic biology and artificial intelligence to manage its complex ecological interactions. The facility operated with no external inputs other than sunlight for 5 years, a record at the time, before requiring minor adjustments to its biogeochemical cycles. The lessons learned from Biosphere 3 informed development of the first true spacecraft-scale closed-loop life support system, tested aboard the Lunar Gateway Station beginning in 2063. The Environmental Regeneration and Closed System module demonstrated 99.7% efficiency in water recycling and 98.4% efficiency in atmospheric regeneration over its 3-year operational test. These figures approached the theoretical minimums needed for interstellar missions. Hydroponics and algae cultivation formed the cornerstones of these life support systems. By 2065, agricultural scientists had developed specialized crop varieties optimized for space environments, plants with shortened growth cycles, enhanced nutritional profiles, and improved light utilization efficiency. Vertical hydroponic systems allowed for maximum food production in minimal volume, with water and nutrients constantly recycled throughout the system. Similarly, bioreactors cultivating engineered algae strains demonstrated remarkable efficiency in carbon dioxide absorption and oxygen production. The most advanced systems used multiple species working in tandem to create robust ecological networks resistant to collapse. 1 cubic meter of properly maintained algae cultures could support the respiratory needs of an adult human indefinitely, provided sufficient light energy. The challenge of artificial gravity saw equally significant progress during this period. Early space stations had confirmed the debilitating effects of prolonged weightlessness on human physiology, bone loss, muscle atrophy, cardiovascular deconditioning, and vision problems among them. Any interstellar mission would require effective countermeasures to maintain crew health. The solution, long understood in theory but challenging to implement, was rotation. By spinning a habitat, centrifugal force could simulate gravity along its outer rim. In 2066, the Centrifuge Habitat Demonstration Module was added to the OAP. This 100-meter diameter ring, rotating at 3 revolutions per minute, created Earth-normal gravity along its circumference without inducing the vestibular discomfort associated with higher rotation rates. The true test of these technologies came with the initiation of the Long-Stay program in 2070. This ambitious project established a permanently crewed habitat in cislunar space designed to operate autonomously for extended periods. The initial mission plan called for a crew of 12 to remain aboard for 5 years without resupply beyond emergency reserves. The habitat incorporated all the advances in life support, artificial gravity, radiation shielding, and psychological support developed over the previous decades. The Long-Stay 1 mission exceeded its planned duration, ultimately lasting 7 years before the facility received its scheduled crew rotation and resupply in 2077. Throughout this period, the crew remained healthy and productive, demonstrating that humans could indeed thrive in isolated, confined environments for the durations necessary for interstellar missions. More importantly, the mission validated the reliability of the life support and habitat systems, which operated with minimal degradation throughout the extended mission. While these technological advances were impressive, the social and economic dimensions of interstellar exploration proved equally challenging. The financial requirements for developing interstellar capability dwarfed any previous human endeavor. Initial estimates in 2060 suggested a full-scale Alpha Centauri mission would cost approximately $30 trillion, equivalent to roughly a quarter of the annual global GDP at that time. This staggering figure sparked intense debate about funding priorities. Critics argued that such resources could better address pressing terrestrial needs like climate stabilization, poverty, and disease. Proponents countered that the technological spin-offs from interstellar research already benefited humanity through advances in fusion energy, materials science, and closed-loop ecological systems. The debate came to a head during the global funding crisis of 2063, when several key national contributors threatened to withdraw from the Alpha Centauri mission directorate. The situation was resolved through the Interstellar Dividend Agreement, which established a formal mechanism for commercializing technologies developed for the mission. A percentage of revenues from these spin-off technologies would be reinvested in the mission itself, creating a partially self-sustaining funding model. This period also saw the expansion of human presence throughout the solar system, providing crucial testing grounds for technologies and social systems relevant to interstellar travel. The first permanent Mars colony, established in 2057, grew to a population of over 5,000 by 2070. These colonists developed expertise in operating closed ecological systems and maintaining technological infrastructure with minimal external support, directly applicable skills for future interstellar missions. Similarly, research outposts established on Jupiter's moons in the late 2060s provided experience with the radiation environment and communication delays that would characterize deep space missions. These facilities also began preliminary extraction of helium-3 from Jupiter's atmosphere using specialized atmospheric skimmers, securing a vital resource for advanced fusion propulsion. The governance of these extraterrestrial settlements offered valuable insights into the social structures needed for long-duration space missions. The Mars Colonial Charter of 2062 established a novel form of democratic governance adapted to the constraints and realities of off-Earth habitation. Its emphasis on consensus building, resource stewardship, and technical competence would later influence the organizational structures proposed for interstellar missions. By 2068, the psychological dimensions of interstellar travel had become a major focus of research. The Mars Psychological Adaptation Study tracked colonists over multiple years, identifying key traits associated with successful long-term adjustment to isolated, confined environments. High resilience, emotional stability, agreeableness, and intrinsic motivation emerged as critical factors. These findings informed the development of psychological screening protocols for future deep space missions. The screening process evolved from simple questionnaires to sophisticated assessment centers, where candidates lived and worked together under simulated mission conditions for months. Artificial intelligence systems monitored group dynamics and individual responses to stressors, identifying optimal crew compositions. These methodologies were first deployed in selecting crews for the long-stay program, contributing significantly to its success. As the year 2075 approached, humanity had made remarkable progress toward interstellar capability. The fundamental technologies required for a mission to Alpha Centauri, advanced propulsion, closed-loop life support, radiation protection, and artificial gravity, had moved from theoretical concepts to working prototypes. The infrastructure needed to construct and launch interstellar craft was taking shape in Earth orbit and beyond. Psychological and social systems to support long-duration missions had been developed and tested in analogous environments. Yet significant challenges remained. The Bifrost propulsion system, while promising, had yet to demonstrate full-scale operation. Life support systems, though greatly improved, still fell short of the near-perfect efficiency required for multi-decade missions. The economic model for funding such an enormous undertaking remained precarious, dependent on technological dividends that might not materialize as expected. Most importantly, the interstellar effort had yet to achieve escape velocity from the constraints of political short-termism. Government funding ebbed and flowed with electoral cycles and competing priorities. The visionary goal of reaching Alpha Centauri, a multi-generational project by definition, struggled to maintain consistent support in political systems designed around much shorter timeframes. Nevertheless, by 2075, the foundation for humanity's first mission to another star had been firmly established. The question was no longer whether such a mission was possible, but when and how it would be accomplished. The next quarter century would see these foundational technologies mature into operational systems capable of bridging the vast distance to our stellar neighbor. As one prominent astronautical engineer remarked at the time, "We are no longer building castles in the air. We are constructing the first bridges to the stars, slowly, methodically, one technological span at a time." Part 3. The Prototype Era. The final quarter of the 21st century marked humanity's transition from theoretical preparation to practical implementation of interstellar technologies. With the foundational science established and key systems demonstrated at small scales, the time had come to build and test actual interstellar-capable hardware. This period would determine whether the dream of reaching Alpha Centauri could be transformed from speculative possibility to engineering reality. The era began with the ambitious Pathfinder program, a series of unmanned missions designed to test fusion propulsion and other critical technologies at progressively greater distances from Earth. Pathfinder 1, launched in 2076, became the first spacecraft to incorporate a functioning fusion drive based on the Rufus 2 design. Using deuterium-helium-3 fuel, the probe demonstrated the sustained operation of its propulsion system during a 10-month acceleration phase, reaching a velocity of nearly 1,000 kilometers per second, far faster than any previous human-made object. This impressive speed allowed Pathfinder 1 to reach Jupiter in just 45 days, compared to the years required by earlier missions. After conducting observations of the Jovian system, the probe continued its outward journey, eventually reaching the orbit of Neptune in early 2078. At this distance of roughly 4.5 billion kilometers from Earth, Pathfinder 1 provided the first real test of communications technologies designed for interstellar distances. Traditional radio communications, which had served space missions adequately within the inner solar system, faced fundamental limitations at greater distances. Signal strength diminishes with the square of distance, requiring either immensely powerful transmitters or extraordinarily sensitive receivers. For truly interstellar communications, even these measures would prove insufficient. Pathfinder 1 carried an experimental X-ray laser communication system capable of transmitting data in a highly focused beam with minimal dispersion. This system successfully maintained a data rate of 10 megabits per second from Neptune's orbit, sufficient for transmitting scientific data and system telemetry. While still inadequate for interstellar distances, this demonstration validated the underlying approach. The mission also tested the first generation of autonomous repair systems, a critical capability for any spacecraft operating beyond hope of human intervention. When a micrometeoroid impact damaged one of Pathfinder 1's radiator panels in late 2077, the onboard maintenance system deployed a specialized repair drone that successfully patched the coolant leak and restored the panel to 92% functionality. This seemingly modest achievement represented a crucial milestone, the first self-repair of a spacecraft in deep space. Pathfinder 2, launched in 2079, built upon these successes with more advanced systems. Its fusion drive incorporated refinements from the Bifrost program, achieving a specific impulse of 850,000 seconds and a peak velocity of 1,500 kilometers per second. This mission targeted the outer edge of the solar system, aiming to reach the heliopause, the boundary where the sun's influence gives way to true interstellar space. The most significant innovation aboard Pathfinder 2 was its advanced artificial intelligence for mission management. Previous space missions had relied on pre-programmed responses to anticipated situations, supplemented by commands from human controllers on Earth. But as communication delays stretched from minutes to hours and eventually days, this approach became increasingly impractical. The Adaptive Mission Intelligence System, or AMIS, represented a fundamental shift in spacecraft autonomy. Rather than following fixed protocols, AMIS could assess novel situations, weigh multiple response options, and implement solutions based on mission priorities and available resources. The system combined neural networks, trained on millions of simulated mission scenarios, with symbolic reasoning capabilities that allowed it to explain its decision-making process to human operators when required. When Pathfinder 2 encountered an unexpected radiation phenomenon beyond the orbit of Pluto in 2081, AMIS demonstrated its value by reconfiguring the probe's protective systems and adjusting its trajectory without awaiting instructions from Earth. By the time mission controllers received data about the encounter, the situation had already been successfully managed. This level of autonomy would prove essential for future interstellar missions, where communications delays would stretch to years rather than hours. The culmination of the Pathfinder program came with Pathfinder 3, launched in 2083. This ambitious mission incorporated the most advanced version of the Bifrost propulsion system, achieving a remarkable speed of 2,200 kilometers per second, approximately 0.7% of light speed. While still far short of what would be needed for practical interstellar travel, this velocity enabled the probe to reach the heliopause in just over 2 years, compared to the decades required by earlier missions like Voyager. Pathfinder 3 carried the most sophisticated suite of instruments ever deployed to study the boundary between our solar system and interstellar space. Its measurements revealed unexpected complexities in the structure of the heliosphere and the characteristics of the interstellar medium beyond. These findings would prove crucial in refining the designs of true interstellar vehicles. The probe also tested second-generation repair systems with greater capabilities than their predecessors. Using advanced 3D printing technology, these systems could not only patch damage, but fabricate replacement components from raw materials carried aboard. When one of the probe's sensor arrays failed completely in 2086, the maintenance system successfully manufactured and installed a functional replacement, though with somewhat reduced capabilities compared to the original. While the Pathfinder program pushed the boundaries of fusion propulsion, a parallel effort focused on an entirely different approach to interstellar travel. The Breakthrough Starshot initiative, after decades of development, was finally ready to attempt what had long been its ultimate goal: launching the first human-made objects to another star. In 2085, after extensive testing of all components, the Starshot laser array was activated at full power for the first time. Located in lunar orbit to avoid atmospheric interference, this massive installation generated a combined beam power of 100 gigawatts, comparable to the output of dozens of large power plants. The beam was focused on a formation of 1,000 Starship probes, each weighing just a few grams, and attached to ultra-thin light sails 4 meters in diameter. The launch occurred on July 4, 2085, symbolically chosen to echo the date of American independence centuries earlier. When the laser array fired, the starships experienced acceleration of nearly 10,000 g-forces, reaching 20% of light speed in just under 10 minutes of continuous illumination. At this velocity, the tiny probes would reach Alpha Centauri in approximately 22 years, with arrival expected in 2107. Each starship carried miniaturized scientific instruments, including cameras, magnetometers, and particle detectors. Their primary mission was to conduct a high-speed flyby of the Alpha Centauri system, collecting data on the stars, any planets they might encounter, and the interstellar medium along the way. The probes had no propulsion of their own and no ability to slow down upon reaching their destination. They would zip through the target system in a matter of hours, frantically gathering data to transmit back to Earth. The successful launch of these first true interstellar probes generated unprecedented public excitement. News outlets worldwide carried live coverage of the event, and public viewing parties gathered to witness what many considered a pivotal moment in human history. The knowledge that human-made objects were now traveling to another star seemed to touch something profound in the collective psyche, regardless of nationality or background. This enthusiasm only increased when, 6 months later, the starships transmitted their first significant data. Having by then traveled beyond the orbit of Mars, the probes began detecting variations in the interstellar medium that had not been predicted by Earth-based observations. These findings immediately proved valuable, highlighting previously unknown challenges that would face larger spacecraft following the same trajectory. One such challenge emerged in 2087, when approximately 30% of the Starship swarm abruptly ceased transmitting. Analysis of final telemetry suggested that the probes had encountered a much denser than expected cloud of interstellar dust, resulting in catastrophic impacts at their tremendous velocity. This sobering development underscored the hazards of high-speed interstellar travel and prompted a reevaluation of shielding requirements for future missions. The remaining starships continued their journey, providing a continuous stream of data about conditions in interstellar space. When the lead elements of the swarm crossed the heliopause in 2088, humanity received its first direct measurements of the true interstellar medium, unaffected by the sun's magnetic field and solar wind. These readings indicated higher concentrations of ionized hydrogen than anticipated, with implications for both shielding and propulsion system designs. As the Starship swarm receded into the depths of interstellar space, engineers and scientists turned their attention to the next logical step: designing a much larger spacecraft capable of carrying humans to Alpha Centauri. The conceptual design for this vehicle, designated Pioneer 1, began in earnest in 2089. From the outset, Pioneer 1 was conceived as a modular vessel, composed of discrete sections that could function semi-independently if necessary. This approach offered several advantages. Components could be launched separately and assembled in space. Damaged sections could potentially be isolated to prevent catastrophic failure, and the design could more easily accommodate improvements or replacements as technologies evolved during the extended construction period. The core of the design consisted of 5 primary modules. The propulsion module would house the advanced fusion drive, fuel storage, and related systems. The shield module would lead the spacecraft, providing protection against impacts with interstellar dust and gas. The habitat module would contain the living quarters, life support systems, and artificial gravity ring for the crew. The systems module would house main computing facilities, power generation, and spacecraft control functions. Finally, the science module would contain the research facilities and instrumentation for studying Alpha Centauri upon arrival. Each module was designed with significant redundancy in critical systems. Where possible, backup components would utilize different underlying technologies to avoid common mode failures. For example, primary power generation would rely on advanced radioisotope systems, while backup power would come from fuel cells and advanced photovoltaics. This diversity of approaches meant that no single failure mechanism could disable all power sources simultaneously. Radiation shielding represented one of the most significant design challenges. Interstellar space lacks the protection of Earth's magnetic field, exposing the spacecraft and crew to the full intensity of galactic cosmic radiation and solar energetic particles. Traditional approaches using passive mass shielding would be prohibitively heavy for an interstellar mission. The solution emerged from the Advanced Materials Research Initiative, which in 2092 developed a novel multi-layered shielding system combining several approaches. The outermost layer consisted of a superconducting magnetic shield to deflect charged particles. Behind this came a layer of hydrogen-rich materials to absorb neutron radiation. Next was an electrostatic shield to capture secondary particles generated by interactions with the outer layers. Finally, a water jacket surrounding critical habitation areas provided additional protection for the crew during solar flare events or similar radiation spikes. Testing of prototype shields at the Lunar Radiation Exposure Facility demonstrated that this integrated approach could reduce radiation exposure to levels comparable to those experienced on Earth's surface, a remarkable achievement that removed one of the most serious obstacles to long-duration human spaceflight. Power generation for a century-long mission presented another formidable challenge. Traditional radioisotope systems, which had powered numerous deep space probes, typically degraded significantly after a few decades due to the natural decay of their fuel. Pioneer 1 would require much longer-lived power sources. The breakthrough came with the development of the cascading isotope power system in 2094. This ingenious design utilized a series of different radioisotopes with varying half-lives, arranged so that the decay products of longer-lived isotopes would activate shorter-lived ones over time. This approach allowed for a nearly constant power output over a 200-year period, more than adequate for the mission duration. As the technical design of Pioneer 1 progressed, so too did consideration of the profound ethical questions surrounding such a mission. In 2090, the newly formed United Nations Interstellar Ethics Council convened its first meeting in Geneva. Composed of philosophers, ethicists, scientists, legal scholars, and religious leaders from diverse traditions, the Council sought to establish a moral framework for humanity's first mission to another star. Among the most contentious issues was the question of multi-generational voyages. Given the limitations of even the most advanced propulsion systems, a human mission to Alpha Centauri would likely require decades, possibly exceeding a single human lifespan. This raised profound questions about consent and autonomy for individuals born during the journey who would have no choice in their participation. After 2 years of deliberation, the Council issued its landmark report, Ethical Dimensions of Interstellar Travel, in 2092. The report concluded that multi-generational missions could be ethically justified under specific conditions: fully informed consent from initial crew members, robust governance structures ensuring rights for future generations, guaranteed option to return for those born in transit, and psychological and social support systems to maintain well-being throughout the journey. The report also addressed the critical issue of planetary protection, the obligation to avoid contaminating potentially life-bearing worlds with terrestrial organisms. The Council recommended a tiered approach, with strictest protocols applying to planets deemed most likely to harbor indigenous life. For worlds in Alpha Centauri's habitable zones, this would mean stringent sterilization of all landing equipment and limitations on direct human contact until biological surveys could be completed. Legal considerations proved equally complex. No existing framework of international law had contemplated human activities beyond our solar system. Questions abounded. Who would have jurisdiction over a spacecraft years or decades from Earth? What legal systems would govern crimes or disputes aboard? How would property rights be determined for any resources or discoveries at the destination? The Interstellar Jurisdiction Convention, ratified by 137 nations in 2096, established the first legal framework specifically addressing these issues. The convention created a specialized legal code for interstellar missions, combining elements of maritime law, space law, and diplomatic principles. Under this framework, the spacecraft itself would constitute a distinct legal jurisdiction, with its own governance structures operating under broad principles established before departure. Notably, the convention explicitly recognized the rights of any sentient extraterrestrial life that might be encountered, prohibiting exploitation or harmful interference without informed consent. While many considered this provision largely symbolic, given the unlikely prospect of encountering advanced life forms, it represented an important philosophical commitment to approaching other worlds with respect rather than a purely extractive mindset. By 2098, the conceptual design for Pioneer 1 had been largely finalized, and preliminary construction of test components had begun at the orbital assembly platform. The first full-scale prototype of the habitat module was completed in 2099, allowing for integrated testing of life support, artificial gravity, and crew accommodation systems. Although the prototype lacked the radiation shielding and many redundancies of the final design, it demonstrated the fundamental viability of the concept. Initial estimates suggested that complete construction of Pioneer 1 would require approximately 15 years, with launch conceivably occurring by 2115. With the Starship probes expected to reach Alpha Centauri around 2107, their data would be available in time to make final adjustments to the mission profile and scientific priorities. As the century drew to a close, humanity stood on the threshold of a new era in space exploration. The technological pieces needed for interstellar travel were falling into place. The ethical and legal frameworks to guide such missions had been established, and public support remained strong, bolstered by regular updates from the Starshot probes racing toward Alpha Centauri. Yet significant hurdles remained. The full Bifrost propulsion system had yet to be demonstrated at the scale required for Pioneer 1. The integrated life support and habitat systems would need to prove their reliability over mission-relevant timeframes. And the staggering cost of the endeavor, estimated at over $50 trillion, would require sustained global commitment through changing political landscapes and competing priorities. Nevertheless, as the world entered the 22nd century, the prospect of sending humans to another star no longer seemed an impossible dream. The prototype era had translated theoretical possibilities into working systems, and the path toward Alpha Centauri, while still long and challenging, had never been more clearly defined. The next phase would determine whether humanity could move from prototypes to a full-scale interstellar mission, a challenge not just of technology, but of collective will and shared vision for our species' future among the stars. Part 4: Construction begins. The dawn of the 22nd century marked the transition from planning and prototyping to actual construction of humanity's first interstellar spacecraft. After decades of theoretical work, technological development, and small-scale demonstrations, the time had come to begin assembling the vessel that would carry humans to Alpha Centauri. This monumental undertaking would require unprecedented industrial capacity in space, new construction techniques, and global coordination on a scale never before attempted. The cornerstone of this effort was the expansion of humanity's orbital manufacturing capabilities. The orbital assembly platform constructed in the previous century provided valuable experience, but its scale and location were inadequate for building a vessel as massive as Pioneer 1. After extensive analysis, mission planners selected Earth-Moon Lagrange Point 2, L2, as the ideal location for the new construction facility. This gravitationally stable point beyond the Moon offered several advantages: natural shielding from Earth's radiation belts, proximity to lunar resources, and sufficient distance from Earth to minimize the risk to populations below during testing of the powerful propulsion systems. Construction of the Interstellar Construction Facility, or ICF, began in 2102 with the deployment of the Central Hub Module. Launched from Earth on a heavy-lift vehicle, this 30-meter core structure contained basic life support, power generation, and docking facilities for subsequent modules. Over the following 3 years, additional components arrived from Earth, the Moon, and orbital manufacturing centers, gradually expanding the facility's capabilities and habitable volume. By 2105, the ICF had grown to include specialized fabrication modules, pressurized construction hangars, and accommodation for a permanent crew of 60 workers. The facility's modular design allowed for ongoing expansion as construction requirements evolved. Perhaps most impressive was its integrated robot fleet, over 200 specialized construction units ranging from micro-scale precision fabricators to massive external manipulator arms capable of positioning components weighing hundreds of tons. The logistics of supplying such an enormous undertaking represented a challenge comparable to the construction itself. Materials needed to flow continuously from multiple sources throughout the solar system. Structural elements too large to launch from Earth were manufactured from lunar regolith at the expanded Lunar Industrial Complex. This facility, established in the late 21st century, used solar concentrators to melt and form lunar soil into structural components, taking advantage of the Moon's lower gravity to create large structures that would have been impossible to launch from Earth. Meanwhile, specialized materials like superconductors and advanced composites continued to arrive from Earth. Water for radiation shielding and life support came primarily from near-Earth asteroids, where robotic mining operations had been established during the preceding decades. Perhaps most precious was helium-3 for the fusion drives, harvested from the atmosphere of Jupiter by automated skimmer craft in an operation of breathtaking complexity. All these resources required careful coordination to arrive at the ICF in the proper sequence. The Interstellar Supply Chain Management System, an advanced artificial intelligence, handled this immense logistical challenge, tracking thousands of components and raw materials across millions of kilometers and adjusting delivery schedules to account for the constantly changing orbital mechanics of the solar system. The construction techniques employed at the ICF bore little resemblance to traditional building methods on Earth. In the vacuum of space, with no atmosphere to protect against radiation or temperature extremes, and in microgravity conditions that eliminated the concept of up or down, entirely new approaches were necessary. One revolutionary technique developed specifically for Pioneer 1 was vacuum metallurgy, the process of refining, alloying, and forming metals in the absence of atmospheric contamination. Without oxygen or nitrogen to create impurities, metals produced in this environment achieved unprecedented strength and purity. The largest vacuum metallurgy facility ever constructed operated continuously at the ICF, producing specialized alloys for the spacecraft's critical structural components. Another innovation was the development of in-space additive manufacturing at scales never before attempted. Building on early 21st century 3D printing technologies, the ICF's fabrication modules could deposit materials molecule by molecule according to precise digital specifications, creating components with internal structures impossible to manufacture using traditional methods. This approach was particularly valuable for producing the complex geometries needed for micrometeoroid protection systems and radiation shielding. The labor force that brought Pioneer 1 into existence represented a new paradigm in human-machine collaboration. Human workers, primarily living aboard the ICF for rotations of 6 to 12 months, handled the creative problem-solving aspects of construction and supervised the more routine operations. Their robotic counterparts performed tasks too dangerous, precise, or tedious for humans, from spacewalks lasting weeks to manipulating components at the molecular level. This workforce developed its own unique culture over time, with specialized terminology, social norms, and even art forms emerging from their shared experience. Many workers volunteered for extended rotations, finding meaning in their direct contribution to humanity's greatest voyage. By 2110, when full-scale construction of Pioneer 1's primary components began, the ICF workforce had expanded to 200 humans working alongside nearly 500 advanced robotic systems. The first major component of Pioneer 1 to enter full construction was the habitat ring, the section that would provide living quarters and work spaces for the interstellar crew. Designed as a rotating torus 100 meters in diameter, this structure would generate artificial gravity through centrifugal force, providing an environment approximately equivalent to Earth's gravity along the outer circumference of the ring. The ring's construction began with the central hub, which would remain stationary while the living areas rotated around it. This complex structure housed the axle bearings, transfer mechanisms, and emergency systems that would allow crew to move between the rotating and non-rotating sections of the spacecraft. The precision required for these components was extraordinary. Tolerances measured in micrometers to ensure proper function over decades of continuous operation. From this hub extended 16 spokes, connecting to the outer ring where the crew would live and work. These spokes served multiple purposes: structural support, transportation corridors, and housing for utilities and emergency systems. They were constructed from advanced carbon-titanium composites, offering exceptional strength-to-weight ratios and resistance to the fatigue that would result from decades of rotation. The outer ring itself, with a circumference of over 300 meters, was divided into 8 separate habitat modules. This modular approach provided several advantages: redundancy in critical systems, the ability to isolate sections in case of emergency, and the opportunity to create varied environments within the overall structure. Each module was designed to be largely self-sufficient, with independent life support systems capable of sustaining occupants for extended periods if separated from the rest of the ring. The construction of these habitat modules incorporated lessons learned from decades of space station and planetary outpost development. Interior spaces were designed to minimize the psychological strain of long-duration spaceflight, with carefully calibrated lighting that mimicked terrestrial day-night cycles, living vegetation integrated throughout common areas, and architectural elements that created a sense of spaciousness despite the physical constraints. A particularly innovative feature was the habitat ring's multi-layered hull, incorporating self-healing capabilities for micrometeoroid protection. The outer layer consisted of a sacrificial shield designed to vaporize small particles on impact. Behind this came several layers of flexible ceramic composite that would deform to absorb energy from larger impacts. Most impressive was the innermost layer, containing microencapsulated sealant materials that would automatically deploy if a breach occurred, sealing small punctures within seconds. Water shielding represented another critical element of the habitat design. The outer circumference of each module incorporated a continuous water jacket 2.5 meters thick, providing protection against cosmic radiation while serving as a reserve for the life support system. This water layer required over 12,000 metric tons of water, harvested primarily from C-type asteroids and delivered to the ICF by automated tanker vessels. The logistics of transporting and installing this massive amount of fluid in precise configuration around the habitat ring represented one of the most complex aspects of the construction process. Psychological comfort received as much attention as physical safety in the habitat design. The century of research on human adaptation to confined environments informed every aspect of the living spaces. Communal areas featured high ceilings and dynamic projection surfaces that could display terrestrial landscapes, astronomical phenomena, or interactive art installations. Private quarters, while compact, incorporated personalization options to give each crew member a sense of territory and control. Perhaps most innovative were the wilderness modules, spaces dedicated to simulating natural environments, complete with controlled weather patterns, day-night cycles, and indigenous plant species from Earth. To validate these design elements, a full-scale prototype of one habitat module was completed in 2115 and underwent a 3-year occupancy test with a volunteer crew. This extended evaluation identified numerous refinements that were incorporated into the final design, from acoustic improvements to modifications in air circulation patterns that reduced the accumulation of particulates in certain areas. In parallel with the habitat ring construction, work proceeded on Pioneer 1's propulsion systems, perhaps the most critical and certainly the most energetic components of the interstellar vessel. The advanced Bifrost fusion drive represented the culmination of nearly a century of fusion research, combining elements of magnetic confinement fusion with innovations derived from the laser-supported fusion concepts developed in the previous century. The heart of this system consisted of three primary fusion reactors arranged in a triangular configuration at the stern of the spacecraft. Each reactor contained a toroidal chamber where deuterium-helium-3 fuel would be compressed to temperatures exceeding 100 million degrees Celsius and densities high enough to overcome the electrostatic repulsion between atomic nuclei. At these extreme conditions, fusion reactions would occur, converting a small fraction of the fuel mass directly into energy according to Einstein's famous equation, E equals mc squared. The engineering challenges in constructing these reactors were immense. The plasma containment systems required superconducting magnets of unprecedented strength and precision, cooled to within a few degrees of absolute zero, while operating mere meters from fusion reactions hotter than the core of the sun. The structural components needed to withstand not only the tremendous forces from the magnetic fields, but also the thermal stresses, radiation damage, and micrometeoroid impacts that would accumulate over decades of operation. Construction of these components required specialized facilities that themselves represented engineering marvels. The superconductor fabrication module, added to the ICF in 2112, produced the intricate magnetic coils in a carefully controlled environment free from even the slightest contamination. The radiation test facility, positioned at a safe distance from the main construction site, subjected materials and components to conditions simulating decades of exposure to the radiation environment they would encounter during the interstellar journey. Fuel production for the Bifrost drive represented another monumental undertaking. While deuterium occurs naturally in Earth's oceans in sufficient quantities, helium-3 is extremely rare on Earth. The solution came from Jupiter, where helium-3 exists in the upper atmosphere at concentrations roughly 100 times greater than on Earth. Beginning in 2108, a fleet of automated harvester craft equipped with advanced scooping systems and cryogenic storage facilities began collecting this precious resource, delivering it to processing facilities on Callisto, Jupiter's outermost large moon. From there, refined helium-3 was transported to lunar storage facilities aboard specialized tankers. The lunar storage site, located at the South Pole in permanent shadow, maintained the cryogenic temperatures necessary to keep helium-3 in liquid form. By 2120, sufficient fuel had been accumulated to support multiple round-trip journeys to Alpha Centauri, a stockpile representing the single most valuable material reserve in human history. Testing the propulsion systems presented unique challenges, as a full-power ignition of the Bifrost drive would produce an exhaust plume extending thousands of kilometers. To address this, engineers developed a scaled approach, testing individual components and subsystems before proceeding to integrated tests at progressively higher power levels. The first successful ignition of a complete Bifrost reactor at 5% nominal power occurred in 2121, conducted at a specialized test facility positioned in a wide orbit to minimize risks to other space infrastructure. This test validated the fundamental design while highlighting areas requiring refinement. The plasma containment system showed unexpected instabilities during power transitions, necessitating modifications to the control algorithms. Thermal management proved more challenging than simulations had predicted, requiring additional radiator capacity to dissipate waste heat. Each issue was methodically addressed, with subsequent tests demonstrating improved performance and reliability. Redundancy and emergency systems received particular attention throughout the propulsion system design. Each of the three primary reactors was capable of independent operation, allowing the spacecraft to continue its mission even if one failed completely. Backup systems utilized different technologies where possible to avoid common mode failures. For example, while the primary thrust vectoring relied on magnetic field manipulations, the emergency system used mechanical gimbals that could function even in the event of a complete electrical failure. As construction of Pioneer 1 progressed, the project faced its greatest challenge not from engineering problems, but from changing political and economic circumstances. The global economic realignment of 2122 to 2124, triggered by climate mitigation costs and shifting power dynamics between nations, led to severe budget pressures across all sectors. The Interstellar program, as the single largest coordinated human endeavor, became an obvious target for those seeking to redirect resources toward immediate terrestrial needs. The crisis came to a head in March 2123, when 7 major funding nations announced their intention to reduce contributions to the program by 40 to 60% over the following 5 years. This reduction, if implemented, would have effectively halted construction of Pioneer 1, potentially delaying the mission by decades or canceling it entirely. Public opinion polls showed a populace divided, with support for the program dropping to its lowest levels since inception as economic anxiety intensified. In this moment of existential crisis for the mission, the scientific and space advocacy communities mobilized as never before. The Coalition for Interstellar Exploration, formed by leading research institutions and space agencies, launched a global information campaign highlighting the technological, economic, and inspirational benefits already derived from the program. They emphasized the advanced energy systems, materials, and life support technologies that had transitioned to terrestrial applications, improving life on Earth even as they enabled interstellar travel. Particularly effective was the Dividend Documentation Initiative, which quantified the economic return on investment from specific interstellar technologies. The fusion containment systems developed for Pioneer 1 had already revolutionized terrestrial energy production, eliminating fossil fuel use in numerous countries. Medical technologies created for long-duration spaceflight had extended healthy lifespan by an average of 7 years. Computational advances driven by mission requirements had accelerated progress across fields from climate modeling to drug discovery. As these concrete benefits became better understood by the public and policymakers, sentiment began to shift. Demonstrations in support of the program occurred in major cities worldwide, with particularly strong turnout among younger generations who saw interstellar exploration as integral to humanity's future. The pivotal moment came in November 2123, when a delegation of 200 leading scientists from across the globe addressed the United Nations General Assembly. Their presentation, titled "The Cost of Abandoning the Stars," made a compelling case that the technological ecosystem developed around the interstellar program had become essential to addressing Earth's most pressing problems. Abandoning the mission would not only surrender humanity's greatest aspiration, but would actually impede solutions to immediate challenges like climate stabilization, food security, and public health. The address concluded with the famous Continuity Pledge, in which the assembled scientists committed to donating 15% of their own salaries to support the program if necessary, a powerful symbolic gesture from individuals who were already among the most dedicated to the mission. Following 3 months of intense international negotiations, a resolution emerged in the form of the Interstellar Continuity Agreement of 2124. Rather than cutting funding abruptly, nations would maintain their commitments but extend the construction timeline by approximately 5 years, reducing annual expenditures to more manageable levels during the economic recovery period. Additionally, a new framework was established to more directly integrate technological spin-offs into Earth's economy, with a percentage of resulting revenues flowing back to support the program. To symbolize this renewed commitment, an unprecedented ceremony was held at the Interstellar Construction Facility on July 20, 2124, the 155th anniversary of the first human landing on the Moon. Representatives from all 142 participating nations gathered to sign the continuity agreement in person, conducting the largest diplomatic assembly ever held in space. The event, broadcast live to an estimated 9 billion viewers, featured the ceremonial installation of a component of the habitat ring bearing the signatures of all attendees, a permanent testament to global unity in pursuit of the stars. With the funding crisis resolved, construction of Pioneer 1 resumed its planned trajectory, albeit with a revised completion date of 2130 rather than the original 2125 target. The delay, while disappointing to many within the program, allowed for incorporation of technological improvements developed during the extended timeline, potentially enhancing the mission's overall prospects for success. As 2125 drew to a close, Pioneer 1 had taken visible shape at the Interstellar Construction Facility. The habitat ring was structurally complete and undergoing internal outfitting. 2 of the 3 main propulsion reactors had been installed and successfully tested at 25% power. The command and control systems were operational, running extensive simulations to validate their performance. Initial elements of the radiation shield had been positioned, with the distinctive multi-layered configuration beginning to enclose the forward sections of the vessel. From observatories across Earth, the growing spacecraft was visible as a bright point of light when it caught the sun at the right angle, a new star in a sense, created by human hands and destined to journey to real stars. For those who had dedicated their careers to the interstellar mission, this visible manifestation of their work represented the culmination of lifetimes of effort. For the broader public, it served as a constant reminder that humanity's reach now extended beyond the solar system that had been our only home for all of previous history. The construction of Pioneer 1 represented far more than an engineering project, however impressive its scale. It embodied humanity's determination to expand our presence beyond the solar system, to become, for the first time, a truly interstellar species. The challenges that had been overcome, both technical and political, demonstrated a capacity for long-term thinking and global cooperation that offered hope for addressing other existential challenges facing our species. As one prominent astrophysicist noted during the continuity ceremony, "In building this ship, we have also rebuilt ourselves. We have proven that we can think beyond single lifetimes, beyond national interests, beyond immediate returns." That capacity to work together toward distant horizons may ultimately be more valuable than any destination we reach among the stars. Part 5: Final Preparations. With the physical construction of Pioneer 1 well underway, attention turned to the most critical element of the mission: the crew who would undertake this unprecedented journey. Unlike previous space missions measured in days, months, or even years, the voyage to Alpha Centauri would span decades. Many who departed would never return to Earth, and children born during the journey would know our home planet only through records and stories. The selection of this crew represented perhaps the most complex human resources challenge ever undertaken. The process began in 2127 with the establishment of formal selection criteria by the Interstellar Crew Directorate. Genetic diversity figured prominently among these requirements. To maintain a stable population over multiple generations without risk of inbreeding depression, careful attention to the crew's collective genome was essential. Mathematical models suggested a minimum founder population of 80 individuals with optimized genetic diversity would be necessary, particularly if advanced genetic screening and reproductive technologies were employed to manage subsequent generations. Beyond genetics, psychological factors proved equally important. The initial crew would face unique stresses: confinement within the spacecraft for the remainder of their lives, communication delays with Earth stretching to years, and the responsibility of establishing humanity's first outpost around another star. Traditional astronaut psychological profiles, developed for missions lasting months, proved inadequate for evaluating candidates for such an unprecedented undertaking. The Interstellar Psychological Assessment Protocol, developed specifically for Pioneer 1, evaluated candidates across dozens of dimensions, with particular emphasis on traits like adaptability, frustration tolerance, and intrinsic motivation. Group dynamics received special attention, with candidates undergoing extended isolation studies in groups to identify compatible personalities and effective team structures. By 2130, over 200,000 initial applicants had been narrowed to a pool of approximately 500 finalists. These finalists underwent 3 years of preliminary training before final selections were made. This preparation included specialized skill development across multiple disciplines, ensuring each crew member could perform numerous functions aboard the spacecraft. Cross-training became the norm, with every individual required to demonstrate proficiency in at least 5 critical mission areas such as propulsion engineering, life support maintenance, medical care, agricultural management, and information systems. Perhaps most innovative was the philosophical and spiritual preparation integrated into the training program. Recognizing the profound existential dimensions of the journey, the crew preparation included extensive reflection on meaning, purpose, and humanity's place in the cosmos. Rather than prescribing specific belief systems, the program encouraged each candidate to develop personal frameworks for understanding their role in this historic undertaking. Many candidates reported that this aspect of preparation, initially viewed with skepticism, became among the most valuable as they contemplated the magnitude of the journey ahead. In 2134, mission planners announced the selection of the 85 primary crew members, along with 40 alternates who would continue training for potential late substitutions. The selected group, 44 women and 41 men ranging in age from 26 to 52, represented 38 nationalities and diverse professional backgrounds including engineering, medicine, agriculture, education, and cultural preservation. As the crew prepared for their historic journey, the mission received an invaluable influx of new data from beyond our solar system. The Starshot probes, launched in 2085, had been racing toward Alpha Centauri at 20% of light speed. In 2129, after 44 years of travel, the first signals from these probes finally reached Earth, carrying precious information about our stellar neighbor. The data took another 4.37 years to make the return journey across interstellar space, finally arriving at Earth in early 2134. The signal, though greatly attenuated by distance, contained a treasure trove of scientific measurements and the first direct images of the Alpha Centauri system taken from within its boundaries. Mission specialists worked feverishly to process and analyze the incoming data, extracting every possible insight to inform the final preparations for Pioneer 1. The images of Alpha Centauri A and B, now resolved as distinct stellar disks rather than a single point of light, captivated the public imagination. More significant for mission planners were the detailed measurements of the interstellar medium the probes had traversed. The data confirmed higher than expected densities of ionized hydrogen in certain regions, requiring adjustments to Pioneer 1's shielding configurations. Most exciting were the findings regarding Proxima b, the Earth-sized planet orbiting within Proxima Centauri's habitable zone. Spectrographic analysis confirmed the presence of an atmosphere, though thinner than Earth's. Surface temperature readings suggested conditions potentially compatible with liquid water in equatorial regions, though the planet's likely tidal locking to its star created extreme temperature differentials between its perpetual day and night sides. Unexpected findings about Proxima b's radiation environment prompted the most significant engineering adjustments. The probes detected evidence of more intense stellar flare activity than Earth-based observations had suggested, indicating that the planet received periodic radiation doses substantially higher than Earth norms. This discovery led to enhanced radiation protection for both the crew quarters and for any equipment designed for potential surface operations after arrival. By 2138, implementation of these design modifications was complete, and attention turned to what many considered the mission's most enduring legacy: the knowledge repository. This vast digital archive would serve multiple purposes: educating future generations born during the journey, preserving Earth's cultural heritage, and providing the technical information necessary to establish a human presence in the Alpha Centauri system. The repository's development engaged thousands of specialists across all fields of human knowledge. Historians, scientists, engineers, artists, and philosophers worked to distill humanity's accumulated wisdom into a format that could be efficiently stored, accessed, and understood by generations far removed from Earth. The technical challenges were considerable, requiring storage media that could remain stable for centuries and interface systems that could adapt to evolving technologies. The completed repository contained three main divisions. The scientific and technical archive included comprehensive engineering data, medical knowledge, agricultural techniques, and the accumulated scientific understanding of the universe. The Cultural Heritage Collection preserved representative works of literature, music, visual arts, and philosophy from across human history and all major civilizations. The historical record provided context for humanity's journey to the stars, from our earliest civilizations through the development of space travel and the construction of Pioneer 1 itself. Beyond digital information, the mission incorporated a physical biological archive named the Seeds of Earth. This collection included cryopreserved seeds from thousands of plant species, cellular samples from Earth's biodiversity, and genetic records of species that couldn't be physically transported. While primarily intended for scientific study, this biological heritage also provided the option for limited ecosystem establishment at the destination, should conditions prove favorable. Anthropological considerations guided the development of educational systems for generations that would be born during the journey. These systems needed to transmit not only practical knowledge, but also cultural context that would otherwise be lost without direct experience of Earth. Immersive virtual environments were developed that would allow ship-borne children to visit Earth's landscapes, cities, and historical sites, maintaining a connection to the home planet they would never physically experience. As 2140 approached, Pioneer 1 entered the final integration and testing phase. While individual systems had been extensively tested during development, their interactions within the completed spacecraft presented new complexities. A comprehensive integration protocol verified the proper functioning of all primary and backup systems under normal conditions, then deliberately introduced failures to assess the resilience of the overall design. The mission control team conducted a full-scale simulation of the first decade of the journey in 2142, with the actual crew living aboard the completed habitat ring for 6 months. During this period, they operated all spacecraft systems under conditions mirroring those they would experience during the real mission, including communications delays and unexpected challenges introduced by the simulation directors. This extensive testing identified several unforeseen issues. Interactions between the propulsion cooling systems and habitat environmental controls created unexpected thermal gradients in certain sections of the living quarters. The primary communications array showed occasional interference patterns when the propulsion system operated at high power levels. Most concerning, certain critical components showed higher than predicted wear rates, suggesting they might not meet their designed service life of 100+ years. Engineering teams addressed each issue methodically. Thermal management systems were reconfigured to eliminate the problematic gradients. Communication systems received additional shielding and redundant transmission paths. Components with concerning wear patterns were redesigned using more durable materials or augmented with automated maintenance systems capable of performing replacements during the journey. Crisis scenario training formed another critical element of final preparation. The crew underwent thousands of hours of simulations covering every conceivable emergency. Propulsion failures, micrometeoroid impacts, radiation events, medical crises, social conflicts, and psychological challenges. These scenarios ranged from relatively minor malfunctions to catastrophic failures requiring dramatic interventions. The goal was not only to develop specific response protocols, but to build the crew's collective problem-solving capabilities and resilience in the face of the unknown. By 2145, Pioneer 1 had successfully completed all major test milestones. The vessel was technically ready for departure, awaiting only final loading of consumables and the formal mission commencement. The completed spacecraft represented the most complex machine ever built by humanity, a self-contained world designed to sustain human life across interstellar space for generations. The final 5 years before launch were devoted to last-minute upgrades incorporating the very latest technologies. Advanced neural interface systems were installed in the command centers, allowing for more intuitive control of ship systems. The artificial intelligence supporting life support functions received significant enhancements, improving its predictive maintenance capabilities. The medical facilities were upgraded with the newest regenerative treatment technologies, further reducing dependence on physical supply stockpiles. As 2150 approached, humanity stood on the threshold of becoming an interstellar species. Pioneer 1, gleaming in orbit beyond the moon, represented not merely an extraordinary machine, but the embodiment of our collective aspiration to reach beyond our native star system. The crew, now fully trained and psychologically prepared for their one-way journey, waited for the final launch authorization that would begin humanity's greatest voyage of exploration. The dream that had begun as theoretical discussions in the early 21st century had transformed through decades of research, engineering challenges, political struggles, and testing into a physical reality poised to depart our solar system. The next phase would test not only the technologies developed for this audacious journey, but the human spirit itself, as we reached toward the stars that had beckoned us since the dawn of consciousness. Part 6: The Grand Departure. The day of January 12, 2150 dawned like any other across Earth's time zones, yet it would be remembered throughout human history as the day we became an interstellar species. After more than a century of preparation, Pioneer 1 stood ready to embark on humanity's greatest journey of exploration, the first crewed mission to another star system. The departure ceremony began at exactly 10 o'clock Universal Time, broadcast to an estimated 98% of Earth's population through various media. Television and holographic displays in public squares around the world showed the gleaming spacecraft in its holding position at Earth-Moon L2, its distinctive silhouette, the large forward shield, central habitat ring, and rear propulsion assembly, now familiar to billions. World leaders gathered at mission control facilities on Earth, while cultural representatives, scientists, and family members of the crew participated from various viewing platforms throughout cislunar space. The ceremony integrated elements from dozens of cultural traditions, acknowledging the truly global nature of the endeavor. Ancient rituals of departure merged with modern technological displays in a hybrid celebration that honored both humanity's past and its ambitious future. The crew, having already boarded Pioneer 1 3 weeks earlier for final systems checks, participated in the ceremony from the spacecraft's main observation deck. Their faces, visible on screens around the world, showed the complex emotions of the moment, determination certainly, but also hints of the anxiety and solemnity appropriate to those departing on a one-way journey beyond our solar system. Perhaps the most poignant aspect of the ceremony was the personal farewell messages. Each crew member had the opportunity to say goodbye to family and friends, knowing that while communication would continue for years, they would never again meet in person. These exchanges, despite their intimate nature, were shared with the global audience by mutual agreement, allowing humanity to witness both the personal cost and the profound commitment underlying the mission. One particularly moving moment came when the youngest crew member, a 27-year-old astrobiologist, exchanged final words with her elderly grandparents, who had both worked on early fusion propulsion experiments in the 2090s. Their conversation, bridging generations and connecting the mission's origins to its realization, embodied the long-term vision that had made Pioneer 1 possible. At 12 o'clock Universal Time, precisely on schedule, Pioneer 1 received formal launch authorization. The spacecraft's primary systems transitioned to autonomous operation, severing the last direct control links with Earth-based mission control. While communication would continue, the vessel was now independently responsible for its own operation, a necessary step given the communication delays that would grow as distance increased. The departure itself proceeded in carefully planned stages. Initial separation burns using conventional thrusters moved Pioneer 1 away from its construction dock, creating safe distance for the first ignition of the main propulsion system. For 3 hours, the spacecraft drifted slowly away from Earth-Moon space, conducting final system checks and alignment procedures. At 15:22 Universal Time, Pioneer 1 activated its primary fusion drive at 10% power. The brilliant blue glow of its exhaust plume became visible even to naked-eye observers on Earth, appearing as a new star moving slowly against the background of fixed stars. This modest initial burn would continue for 72 hours, gradually increasing in power as systems were monitored for any anomalies. By January 15, with all systems performing within expected parameters, power was increased to 30% of maximum. The spacecraft now accelerated at approximately 1/10 of Earth's gravity, enough to establish a trajectory that would take it beyond the orbit of Mars within weeks, yet gentle enough to allow for system adjustments if needed. As Pioneer 1 moved beyond cislunar space, the crew began establishing their routines in what would be their permanent home. The rotation of the habitat ring had been initiated before departure, creating artificial gravity equivalent to approximately 80% of Earth normal. This level, chosen after extensive research, balanced the physiological benefits of gravity with engineering constraints and the expectation that any habitable worlds at their destination might have lower gravity than Earth. The interior spaces of the habitat ring, though familiar to the crew from their training, now took on new significance as their permanent community. 8 distinct habitat sectors offered varied environments, from densely vegetated areas reminiscent of Earth's forests to more open, minimalist spaces. Community areas including dining facilities, exercise spaces, and entertainment centers were distributed throughout the ring, while private quarters provided essential personal space. Among the first activities undertaken by the crew was the ceremonial planting in the agricultural sections. Seeds that would provide both practical sustenance and psychological connection to Earth were placed in soil with appropriate ceremony. These initial crops, fast-growing vegetables and grains selected for their nutritional value and cultural significance, would supplement the stored food supplies during the early mission phases, while the full agricultural system established itself. The psychological adjustment to the mission's reality occurred in stages. During the first months, while Earth still appeared as a visible disk through observation ports and communication delays remained under 10 minutes, many crew members reported feeling as though they were on an extended conventional space mission. Only as the blue planet diminished to a bright point of light among the stars did the true nature of their journey begin to manifest psychologically. Mission psychologists had anticipated this transition and implemented a program called Crossing the Threshold, which provided both individual counseling and group activities designed to acknowledge the significance of their departure. Rather than denying the grief that many felt at leaving Earth forever, the program encouraged its healthy expression while simultaneously reinforcing the historic importance of their journey. By June 2150, Pioneer 1 had passed the orbit of Mars, traveling at a velocity approaching 600 kilometers per second and still accelerating. In December of that year, it surpassed the orbit of Jupiter. The spacecraft's speed continued to increase as the fusion drive operated continuously, now at 60% of maximum rated power. These outer planet transits provided valuable scientific opportunities. Although no close approaches were planned, the trajectory was optimized for Alpha Centauri rather than solar system observation. Pioneer 1's advanced sensors gathered data on the giant planets and their moons from perspectives unavailable to Earth-based instruments. The passage beyond Saturn in March 2151 marked another psychological milestone. The ringed planet had traditionally represented the boundary of the familiar solar system for many, and leaving it behind catalyzed discussions among the crew about their place in the cosmos. The ship's observation deck became a popular gathering place during off-duty hours, as crew members contemplated the changing view, Saturn receding behind, the distant star of Alpha Centauri barely distinguishable ahead. By 2153, Pioneer 1 had crossed the orbit of Neptune and entered what astronomers considered the outer solar system. The fusion drive now operated at 90% of maximum power, accelerating the spacecraft at a steady 0.15 gravity. At this point, their velocity exceeded 1,200 kilometers per second, about 0.4% of the speed of light. While modest compared to their eventual cruise velocity, this already made Pioneer 1 by far the fastest human-made object in history. As distance from Earth increased, communication became an escalating challenge. The delay had grown from minutes to hours, making conversational exchanges increasingly difficult. Video calls with family members, once conducted with only minor accommodations for lag, became more like recorded messages exchanged in turn. This growing isolation necessitated the development of new communication protocols. The Interstellar Communication Prioritization System, implemented in 2154, categorized all transmissions based on urgency and importance. Technical data, scientific information, and critical personal messages received highest priority, ensuring they would be transmitted with maximum reliability and minimal compression. Lower priority content, entertainment, general news, and routine correspondence underwent more aggressive compression or waited for favorable communication windows. Artificial intelligence systems on both Pioneer 1 and Earth played crucial roles in this communication ecosystem. They predicted which information would be most valuable to the distant party, prepositioned critical data to minimize perceived delays, and reconstructed degraded transmissions using contextual analysis. Without these systems, meaningful communication across such distances would have been practically impossible. The final live video connection with Earth occurred on November 10, 2155. By this point, the one-way transmission delay exceeded 14 hours, making even the semblance of real-time interaction impossible. The event was structured as a ceremonial transition rather than a true conversation, with both Earth and Pioneer 1 broadcasting prepared statements and cultural performances. Billions watched as Pioneer 1's crew gathered in their main assembly area, performing music and sharing reflections on their journey thus far. From Earth, a global concert featured musicians from every continent performing pieces composed specifically for the occasion. The event concluded with simultaneous renditions of Voyager's anthem, a piece composed in the 2120s that had become unofficially associated with the interstellar mission. This final broadcast marked the transition to a new communication paradigm. Henceforth, transmissions would be packaged as complete data bundles, sent at regular intervals regardless of content. Personal messages, scientific data, cultural updates, and news would all travel together in these consolidated transmissions, optimized for the growing distances involved. The psychological impact of this communication shift proved significant. Many crew members reported heightened feelings of isolation after the ceremonial broadcast, even though the practical change in communication had been gradual. Some described it as the moment they truly left Earth behind psychologically as well as physically. Mission planners had anticipated this reaction, and implemented several countermeasures. The Interstellar program encouraged crew members to focus on building their own community rather than maintaining Earth connections. New creative projects, sporting competitions, and research initiatives provided engaging alternatives to Earth-focused communication. Particularly successful was the New Traditions Initiative, which established cultural practices unique to Pioneer 1, giving the community a strengthened internal identity. In 2158, as Pioneer 1 approached the heliopause, the boundary where the solar wind gives way to the interstellar medium, the mission faced its first major crisis. The spacecraft had reached approximately 120 astronomical units from the Sun and was traveling at nearly 2% of light speed when disaster struck without warning. A micrometeoroid, estimated at just 0.3 millimeters in diameter, but traveling at a relative velocity of over 50 kilometers per second, penetrated the outer hull of Habitat Section 3. At such speeds, the tiny particle carried energy equivalent to a small explosive device. It punched through the external debris shield, the primary hull, and two internal bulkheads before fragmenting in a storage area. Automatic systems detected the breach instantly, sealing the affected compartments and triggering the emergency response protocol. Damage assessment drones deployed within seconds, transmitting detailed imagery of the affected areas to the command center. Meanwhile, the ship's AI tracked atmospheric pressure throughout adjacent sections, identifying even microscopic leaks that might not be immediately visible. The crew's emergency response teams mobilized with efficiency that reflected their extensive training, while engineering teams donned pressure suits to investigate the breach directly. Life support specialists rerouted atmospheric systems to maintain pressure in surrounding areas. Medical personnel stood by, though fortunately no crew members had been in the immediate vicinity of the impact. Within 20 minutes, the situation had been fully assessed. The primary damage was confined to 3 compartments, with secondary damage to electrical and fluid systems serving those areas. Most critically, the micrometeoroid had severed a secondary coolant line, causing a leak of the specialized thermal regulation fluid used throughout the habitat ring. The repair operation proceeded in methodical phases over the next 72 hours. First, temporary patches sealed the hull breach using a rapid hardening composite specifically designed for emergency repairs. Next, damaged systems were isolated and bypassed to restore essential functions to adjacent areas. Finally, permanent repairs began, utilizing the onboard manufacturing facilities to produce replacement components for damaged systems. This incident, while alarming, demonstrated the effectiveness of Pioneer 1's multiple redundancy design philosophy. Despite significant localized damage, no critical systems were compromised beyond repair. The habitat ring maintained overall structural integrity, and environmental systems adjusted automatically to compensate for the damaged sections. More importantly, the crisis provided a crucial test of the crew's self-reliance. For the first time, they faced a potentially catastrophic emergency without any possibility of timely assistance from Earth. By the time news of the incident reached mission control, the crew had already implemented emergency measures and begun repairs. When Earth's response finally arrived 36 hours later, it largely confirmed the actions already taken. The successful navigation of this crisis transformed the crew's collective psychology. Many reported a new sense of confidence in their ability to handle the unknown challenges that surely awaited them in the decades ahead. The theoretical self-sufficiency that had been designed into the mission became a lived reality, strengthening their identity as a distinct, capable community rather than distant extensions of Earth. In the aftermath of the micrometeoroid incident, several important modifications were implemented. The SHIELD tracking system, designed to detect larger objects in the spacecraft's path, was recalibrated to improve sensitivity to smaller particles. Repair procedures were refined based on the actual experience, with several processes simplified to reduce response time. Additionally, crew rotation through potential impact zones was adjusted to minimize exposure in the highest-risk areas identified by new computer modeling. By 2160, Pioneer 1 had fully crossed the heliopause and entered true interstellar space. The propulsion system continued to function flawlessly, gradually accelerating the spacecraft toward its cruise velocity of 12% of light speed, a speed that would allow it to reach Alpha Centauri within the expected lifetime of many of the original crew members. As the vessel moved beyond the sun's immediate influence, crew members gathered at observation ports to witness a sight no humans had seen before: a truly black sky, unaffected by the scattered light of our sun, with the stars showing a clarity impossible within the solar system. Behind them, the sun had diminished to merely the brightest star in the sky, while ahead, Alpha Centauri remained just a point of light, indistinguishable to the naked eye from the stars surrounding it. In this profound moment, many reflected on the unprecedented nature of their journey. They had now traveled farther from Earth than any humans in history, and each day would set a new record for our species' reach into the cosmos. The solar system, home to all human existence until this mission, was now visibly just one small region in the vastness of space, and they were the first to truly leave it behind. As the 22nd century approached its halfway point, Pioneer 1 continued its steady acceleration into the void between stars, carrying with it humanity's first true interstellar community and our shared dream of reaching distant worlds. The greatest journey in human history was well and truly underway. Part 7, The Long Voyage. By the year 2200, Pioneer 1 had settled into its cruising configuration. The main propulsion system, having operated continuously for nearly 5 decades, had accelerated the spacecraft to its designed cruise velocity 12% of the speed of light. At this remarkable speed, the vessel traveled over 35 million kilometers per hour, covering a distance equivalent to Earth's orbit around the Sun in less than 2 days. With maximum velocity achieved, the engineering team executed the long-planned transition to cruise phase operations. The main fusion reactors were powered down to minimum levels, with just enough output to maintain essential systems and provide a small continuous thrust to compensate for the slight drag caused by interstellar hydrogen. This operational shift marked the beginning of the longest phase of the journey, the 5-decade cruise through interstellar space. Daily life aboard Pioneer 1 at cruising speed developed its own unique rhythms. The 24-hour Earth day remained the standard chronological measure, maintained through the ship's lighting systems that mimic terrestrial day-night cycles. The crew work schedule operated on a modified 6-day week, with 4 days of primary duties followed by 2 days for personal projects, recreation, and community activities. The habitat ring's rotation continued to provide artificial gravity, creating an environment where normal human movement remained possible. This proved crucial for maintaining both physical health and psychological well-being. The carefully calculated 80% Earth normal gravity allowed for comfortable existence while reducing structural stresses on the spacecraft and preparing the crew for the possibility of lower gravity environments at their destination. Social structures evolved significantly during these years of stable transit. The initial mission hierarchy, with clearly defined leadership roles and specialized teams, gradually gave way to more fluid organizational patterns. As crew members mastered multiple disciplines through cross-training and education programs, rigid specializations became less relevant. By 2210, the operational model had transformed into what mission sociologists termed a competency collective, where leadership for specific tasks shifted based on relevant expertise rather than fixed positions. This evolution extended to governance systems as well. The original mission charter had established a governing council of 7 members, selected from department heads with a rotating chairperson. By 2215, this had evolved into a more participatory model, where policy decisions were developed through broader consultation before formal ratification. The shipboard assembly, convening monthly with representatives from each habitat section, became the primary forum for community-wide deliberation. Central to ship culture was the research program that continued throughout the interstellar transit. Far from being merely passengers on a long journey, the crew engaged in an ambitious scientific agenda across multiple disciplines. The unique environment of deep space, combined with the specialized facilities aboard Pioneer 1, enabled investigations impossible anywhere else. The Physics Research Group conducted ongoing studies of cosmic rays unfiltered by planetary magnetic fields or atmospheres. Their observations revealed previously undetected patterns in high-energy particle distribution, contributing to refined models of galactic structure. The specialized Cosmic Ray Observatory, positioned on the forward shield of the spacecraft, gathered data of unprecedented quality, given its location beyond the heliosphere. Biological sciences flourished as well, particularly in studying long-term adaptation to the space environment. The controlled ecosystem of Pioneer 1 represented an evolutionary laboratory where multiple generations of organisms, from microbes to plants to small animals, could be observed adapting to space conditions. By 2220, researchers had documented significant adaptive changes in over 200 species, providing insights into evolutionary mechanisms under novel selective pressures. Perhaps most significant were the medical advances emerging from the mission's health maintenance program. The comprehensive monitoring of crew health, combined with the necessity of treating all medical conditions with onboard resources, spurred innovations in preventive care, diagnostics, and treatment. The regenerative medicine techniques developed to address radiation damage and microgravity effects eventually became applicable to a wide range of conditions, creating a valuable knowledge base transmitted back to Earth. These research programs provided more than scientific value. They gave purpose and meaning to the long journey. Crew members could see their work contributing to human knowledge even as they traveled between stars, maintaining connection with the broader scientific enterprise despite their physical isolation. The year 2207 marked a milestone in human history, the birth of Ashley Fenton, the first human born in interstellar space. Her arrival, coming after careful planning and preparation by the ship's medical team, represented a profound transition for the mission. Pioneer 1 was no longer merely carrying Earth-born humans to another star. It had become the cradle for the first generation of humans who would know no home but the ship, and eventually, the Alpha Centauri system. Ashley's birth was followed by others, with 17 children born between 2207 and 2215. This first cohort of ship-born humans presented unique educational challenges. How should children be taught about a home planet they would never experience directly? What skills would be most relevant for lives spent entirely in space or at Alpha Centauri? How could Earth's diverse cultural heritage be meaningfully transmitted to those who would never walk its surface? The Educational Development Team had anticipated these questions, spending years designing learning systems specifically for shipborne generations. The curriculum balanced practical skills necessary for spacecraft operations with broader knowledge of human history, science, arts, and philosophy. Virtual reality environments played a crucial role, allowing children to experience Earth's diverse ecosystems, cities, and historical sites through immersive simulations drawn from the knowledge repository. By 2220, the shipborne population had grown to 32, ranging from infants to teenagers. As the oldest began taking on limited responsibilities within the ship community, cultural transmission challenges became increasingly apparent. Certain concepts, open skies, flowing rivers, changing seasons, remained abstract despite the best educational efforts. Conversely, these young people possessed an intuitive understanding of spacecraft systems, three-dimensional movement, and closed-cycle ecological thinking that their Earth-born parents had acquired only through training. Perhaps most fascinating was the emergence of a distinct philosophical identity among the shipborn. By their teenage years, many expressed a worldview that mission anthropologists termed cosmic citizenship, an identity rooted not in terrestrial nations or cultures, but in humanity's place among the stars. Earth represented their ancestral home deserving of respect, but their primary loyalty lay with the mission community and its purpose of establishing human presence around another star. This perspective sometimes created tensions with the Earth-born crew, who generally maintained stronger emotional connections to their planet of origin. Intergenerational discussions became common in community forums, with shipborne youth questioning certain Earth-centric traditions and perspectives. The annual Earth Day observance, for instance, evolved to include recognition of Ship Day as of equal significance, honoring Pioneer 1 as both vessel and homeland. The shipborne generation also developed distinctive cultural expressions, from art that explored themes of transit and liminality to music incorporating rhythms of shipboard systems. A new dialect emerged, blending elements from the multiple languages spoken aboard with technical terminology and novel expressions describing experiences unique to their environment. By 2230, this linguistic evolution had progressed to the point where communication guides were created to help Earth-born crew members understand certain shipborne expressions. As Pioneer 1 continued its journey through the void between stars, the scientific sensors continued gathering data about the surrounding interstellar medium. This region of space, once thought to be nearly empty, revealed surprising complexity. Variations in dust and gas density created distinct weather patterns through which the spacecraft traveled. These patterns, impossible to detect from Earth-based observations, provided new insights into the structure and dynamics of our galactic neighborhood. One particularly significant discovery came in 2218, when Pioneer 1 encountered an unexpected region of heightened magnetic field strength, extending for nearly 2 light months along its path. This structure, later named the Lowell Ribbon after the scientist who first identified its pattern in the ship's data, appeared to be a remnant of an ancient supernova shockwave. Its discovery prompted substantial revision of models describing interstellar magnetic field distribution. The spacecraft's unique vantage point also enabled groundbreaking astronomical observations. Freed from Earth's atmosphere and the interfering effects of the Sun's heliosphere, Pioneer 1's telescopes achieved unprecedented clarity. The ability to make observations from points spanning light months and eventually light years created opportunities for extreme baseline astronomy, allowing three-dimensional mapping of relatively nearby cosmic structures with extraordinary precision. In 2227, these capabilities led to the first definitive detection of a Kuiper belt-like structure around another star system. The observation of this distant debris disk confirmed long-standing theories about the universality of such features around main-sequence stars and provided comparative data to better understand our own solar system's formation. Shipboard scientific breakthroughs extended beyond observational astronomy. The controlled environment of Pioneer 1 provided ideal conditions for certain types of experiments, particularly in materials science. The extended periods of stable microgravity available in non-rotating sections allowed for the creation of novel alloys and crystalline structures impossible to produce under Earth's conditions. By 2235, the materials laboratory had synthesized over 200 compounds with properties specifically optimized for space applications, including radiation-resistant electronics and ultra-efficient thermal regulators. Transmitting these discoveries back to Earth presented continuing challenges as distance increased. By 2230, the one-way communication delay exceeded 10 years, making even the concept of a conversation with Earth meaningless. Instead, Pioneer 1 broadcast regular data packages containing scientific findings, technical developments, artistic creations, and personal messages. These transmissions used increasingly sophisticated compression algorithms to maximize the information content within the available bandwidth, prioritizing scientific data and technical innovations with potential applications on Earth. Despite the communication challenges, the mission maintained a deep commitment to sharing its discoveries with humanity's home world. Many aboard found meaning in the knowledge that their work would eventually reach Earth, even if they would never know how it was received or applied. This connection to the broader human enterprise helped mitigate the psychological impacts of their physical isolation from the species' birthplace. In 2238, as Pioneer 1 approached the midpoint of its journey to Alpha Centauri, the mission faced its most severe crisis. What began as a minor temperature fluctuation in environmental control subsection 3B cascaded within hours into a catastrophic failure, affecting an entire habitat section housing 43 crew members. The initial malfunction appeared in a thermal regulation junction where multiple coolant systems converged. A microscopic stress fracture, possibly dating back decades to the original construction, finally gave way under pressure. The resulting coolant leak damaged nearby electrical systems, triggering a cascade of failures in the environmental control network. Automated safety systems initially contained the situation, sealing affected compartments and rerouting essential services. However, the complexity of the interconnected systems led to unforeseen complications. As backup systems activated, power surges occurred in secondary distribution nodes, damaging additional components and expanding the affected area. Within 6 hours, the environmental systems for 1/8 of the habitat ring had failed completely. The emergency response mobilized every available crew member with relevant skills. Engineering teams worked in pressure suits as temperatures in the affected sections first rose dangerously high, then plummeted as heating systems failed. Medical personnel established triage centers in adjacent sections to treat injuries ranging from burns to frostbite suffered during evacuation efforts. Despite the rapid response, the situation deteriorated further when a primary atmospheric processing unit suffered catastrophic failure, releasing toxic gases into several compartments. Emergency breathing apparatus saved many, but 7 crew members in the immediate vicinity were overcome before they could reach safety. These were the mission's first casualties since departure, a profound shock to a community that had experienced decades without life-threatening emergencies. For the next 14 days, the crew worked around the clock to stabilize affected systems and prevent further spread of the cascading failures. Drawing on emergency protocols and their years of training, they systematically isolated damaged components, established temporary life support networks, and began the painstaking process of diagnosing the full extent of the damage. The ship's manufacturing facilities operated continuously, producing replacement parts for critical systems. After the immediate crisis was contained, the painful task of honoring the fallen crew members began. The mission had established protocols for space burials, respecting both practical necessities and the cultural and religious diversity of the crew. In a solemn ceremony attended by the entire ship's complement, the bodies of the 7 who had perished were committed to the void, launched in specially designed capsules that would eventually be consumed by the interstellar medium. The memorial service incorporated elements from multiple Earth traditions, while also reflecting the unique culture that had developed aboard Pioneer 1. The ship's choir performed pieces composed specifically for the occasion, while representatives from various ship communities offered reflections on the contributions and legacies of those lost. Most moving was the Remember Earth recitation, where biographical details of each person were shared, connecting their ship lives with their terrestrial origins. The recovery phase lasted well beyond the immediate repairs. Habitat Section 3 required almost complete rebuilding of its environmental systems, a process that took 2 years to fully complete. During this time, the displaced residents were accommodated throughout other sections, straining resources and testing the community's cohesion. Housing arrangements were reconfigured multiple times as repairs progressed, gradually allowing people to return to their homes or to newly assigned quarters. Beyond the technical recovery, the psychological impact of the crisis reverberated throughout the ship community. For decades, daily life aboard Pioneer 1 had proceeded with relative predictability and safety. The sudden loss of 7 lives shattered this sense of security, confronting everyone aboard with the inherent dangers of their unprecedented journey and the ultimate fragility of their artificial world. Mission psychologists had prepared for such events, but still found themselves challenged by the scale of the collective trauma. Group processing sessions became a regular fixture in all ship sections, providing spaces for communal grief while reinforcing mutual support networks. The Memorial Garden, established in one of the agricultural domes, became an important site for reflection and remembrance, with plants chosen to represent the home regions of those who had been lost. Remarkably, the long-term response to the tragedy ultimately strengthened the mission community. The shared experience of crisis, loss, and recovery deepened bonds between crew members across generations and specialties. The successful rebuilding effort demonstrated the community's resilience and self-sufficiency, reinforcing confidence in their collective capability to overcome challenges. By 2242, ship sociologists noted a measurable increase in community cohesion metrics compared to pre-crisis baselines. Technical outcomes proved similarly constructive. The comprehensive investigation into the causes of the cascading failures identified several systemic vulnerabilities in the original design. This led to a ship-wide retrofit program implementing new redundancies, isolation protocols, and early detection systems. The manufacturing capacity of Pioneer 1, originally designed primarily for routine maintenance, was significantly expanded to support more extensive fabrication of replacement components. Perhaps most significant was the knowledge management revolution that followed the crisis. The investigation revealed that subtle warning signs had appeared in various systems for years before the failure, but the connections between these indicators had not been recognized. In response, the mission developed the Integrated Systems Monitoring Framework, a sophisticated analytical platform that correlated data across all ship systems to identify potential failure patterns before they became critical. This innovation was later recognized as one of the mission's most valuable technical contributions, with applications extending far beyond spacecraft management. By 2250, Pioneer 1 had traveled approximately half the distance to Alpha Centauri. The ship community had grown to include over 120 individuals, with shipborne members now outnumbering the original Earth-born crew. The culture aboard had evolved into something unique, neither purely terrestrial nor entirely novel, but a distinctive synthesis reflecting both the mission's Earth origins and its interstellar context. The scientific research program continued to yield valuable discoveries. The technical systems had demonstrated their resilience through crisis and recovery, and the social structures had proven robust enough to support a multi-generational journey. As the ship crossed the midpoint of its journey, attention increasingly turned toward the destination that grew gradually brighter ahead, Alpha Centauri, the star system that would become humanity's second home. For the first time, telescopic observations could resolve distinct details of the system unavailable from Earth. The binary pair of Alpha Centauri A and B showed their distinctive stellar disks, while the planets orbiting them, some known from Earth observations, others newly discovered from the approaching spacecraft, emerged from the glare of their parent stars. Proxima Centauri, the small red dwarf that was their primary destination, revealed more of its planetary system as imaging technology aboard Pioneer 1 captured increasingly detailed views. After a century of travel, the mission had entered its second major phase. The long interstellar cruise was giving way to the approach and preparation for arrival at humanity's new frontier among the stars. Part 8: Arrival and New Beginnings. The year 2250 marked the beginning of Pioneer 1's deceleration phase, the final major stage of its century-long journey to Alpha Centauri. After decades of relative stability during the interstellar cruise, activity throughout the vessel intensified as preparations began for arrival at humanity's new stellar frontier. The engineering challenge of slowing a spacecraft traveling at 12% of light speed was nearly as formidable as the initial acceleration had been. The deceleration maneuver required precise reversal of the main propulsion array, reorienting the vessel so that its engines faced the direction of travel. This complex procedure began in March 2251, carefully executed over a 2-week period to maintain habitat ring stability and minimize disruption to shipboard systems. With the reorientation complete, the main fusion drives ignited at 30% power, producing thrust directly opposite to the spacecraft's velocity vector. The familiar vibration of the engines, absent during the long cruise phase, returned throughout the vessel, a constant reminder that the mission had entered its final approach. Over the next 5 years, power would gradually increase to maximum thrust, creating a deceleration force that would eventually bring Pioneer 1 into the Alpha Centauri system with a manageable velocity for orbital insertion. As the deceleration proceeded, the ship's observation systems underwent comprehensive recalibration and enhancement. Telescopes and sensors that had spent decades studying the distant universe now focused exclusively on the approaching star system. Special filters were installed to manage the increasing brightness of Alpha Centauri's stars, while high-resolution imaging arrays were brought online to capture unprecedented detail of their destination. The growing excitement aboard Pioneer 1 was palpable as Alpha Centauri transformed from a distant point of light to a visibly distinct triple star system. By 2255, with the spacecraft still more than 2 light-years from arrival, shipboard telescopes could resolve features impossible to see from Earth. The binary pair of Alpha Centauri A and B, similar in size and spectral class to our Sun, showed distinct stellar disks and surface features including starspots and prominences. Proxima Centauri, though much smaller and dimmer, revealed its own unique characteristics, including the powerful flare activity typical of red dwarf stars. Most captivating were the first detailed images of planetary bodies within the system. While the existence of several planets had been confirmed from Earth-based observations and early Starshot probe data, Pioneer 1's advanced instruments provided unprecedented clarity. By 2257, the ship's imaging systems had identified 18 substantial planetary bodies across the system, 7 orbiting Alpha Centauri A, 6 around Alpha Centauri B, and 5 circling Proxima Centauri. The flagship discovery was undoubtedly Proxima B, the Earth-sized world orbiting within Proxima Centauri's habitable zone. Early spectroscopic analysis confirmed the presence of an atmosphere containing nitrogen, oxygen, and water vapor in proportions suggesting potential habitability. Most exciting was the detection of absorption patterns consistent with chlorophyll-like compounds, not definitive proof of life, but highly suggestive of photosynthetic activity on the planet's surface. These observations transformed abstract mission objectives into visible reality. Throughout Pioneer 1, display screens showed increasingly detailed images of their destination. The shipborne generations, who had known Alpha Centauri only through educational materials and low-resolution images, were particularly affected. For them, the approaching star system represented not a distant scientific target, but their future home, the place where they would establish humanity's first presence beyond our solar system. By 2265, Pioneer 1 had crossed the traditional outer boundary of the Alpha Centauri system, defined as the point where the gravitational influence of its stars began to exceed that of the Sun. Though still more than 100 billion kilometers from the central binary pair, the spacecraft had officially arrived in humanity's second star system. The momentous crossing was marked with a ceremony in the ship's central assembly area, where representatives from every section gathered to commemorate the achievement. The deceleration continued with increasing intensity as Pioneer 1 approached the heart of the system. By 2270, the main engines operated at maximum power, producing a constant 0.2 gravity deceleration that noticeably increased the effective gravity within the habitat ring. Fuel consumption rates, carefully monitored throughout the journey, remained within projected parameters, ensuring sufficient reserves for the complex maneuvering that would be required within the system. Navigation within a triple star system presented unprecedented challenges. Unlike our solar system, with its single dominant gravitational center, Alpha Centauri required continuous calculation of the complex gravitational interactions between 3 stars and multiple planets. The ship's navigation AI dedicated 40% of its computational capacity to constantly updating trajectory projections, accounting for gravitational perturbations from all significant bodies in the system. The initial approach targeted the Alpha Centauri A and B binary pair, though Proxima Centauri and its potentially habitable planet were the ultimate destination. The mission plan called for a close observational pass of the main binary first. This approach offered several advantages: more detailed study of these sun-like stars than possible from a distance, the opportunity to refine gravitational models of the system through direct measurement, and the option to use gravitational assistance from the stars to adjust the final trajectory to Proxima Centauri. In October 2274, Pioneer 1 made its closest approach to Alpha Centauri A, passing within 60 million kilometers of the star, slightly closer than Mercury orbits our Sun. From this vantage point, the star filled nearly 30 degrees of the sky as seen from the ship, its brilliance requiring specialized filters for direct observation. Every instrument aboard was trained on the star and its planetary system, gathering terabytes of data per hour on magnetic field structures, stellar composition, and planetary characteristics. The 7 planets of Alpha Centauri A revealed themselves as a diverse family ranging from scorched inner worlds to frozen outer bodies. Most notable was the 3rd planet, a super-Earth approximately 1.8 times Earth's diameter orbiting near the inner edge of the star's habitable zone. Spectroscopic analysis detected water vapor in its atmosphere, along with nitrogen and carbon dioxide, suggesting conditions potentially amenable to life. Surface temperature estimates indicated a warm but not extreme climate, with average temperatures perhaps 10 to 15 degrees higher than Earth norms. 3 months later, Pioneer 1 completed a similar observational pass of Alpha Centauri B. This slightly smaller, cooler star hosted 6 detected planets, including 2 within its habitable zone. The 4th planet, similar in size to Mars, showed particular promise with spectroscopic evidence of water-carved surface features. However, its thinner atmosphere and more extreme seasonal variations suggested less favorable conditions for complex life compared to the habitable worlds around Alpha Centauri A. These close stellar passes yielded scientific data of unprecedented detail, including the first measurements of stellar wind and magnetic field structures from within another star system. The planetary observations alone represented a revolutionary advance in exoplanet science, providing ground truth to validate and refine the remote observation techniques used from Earth. With the binary pair survey complete, Pioneer 1 initiated its final transit to Proxima Centauri. Despite being considered part of the same star system, Proxima orbits approximately 0.21 light-years, about 13,000 astronomical units, from the central binary, a vast distance requiring another 5 years of travel time. The ship's velocity, significantly reduced by the long deceleration phase, now allowed for more detailed observations of the interstellar medium within the Alpha Centauri system itself. One significant discovery during this transit was the detection of a complex asteroid belt between the binary pair and Proxima Centauri. This region, likely shaped by the competing gravitational influences of the 3 stars, contained millions of objects ranging from dust particles to small planetesimals. Analysis suggested these bodies were rich in water ice and organic compounds, potentially offering valuable resources for future human settlement in the system. As Pioneer 1 approached Proxima Centauri, anticipation focused increasingly on Proxima B, the Earth-sized world orbiting in the habitable zone of the small red dwarf star. This planet, first detected from Earth in 2016 and studied more closely by the Starshot probes, represented humanity's first opportunity to directly investigate a potentially habitable world beyond our solar system. By early 2280, Pioneer 1 had decelerated to a velocity that would allow for orbital insertion around Proxima Centauri and its planets. The ship's telescopes provided increasingly detailed views of Proxima b, revealing a world of striking contrasts. As a tidally locked planet, it presented the same face to its star at all times, creating permanent day and night hemispheres with extreme temperature differentials. Most intriguing was the terminator zone, the twilight band between the day and night sides, where temperatures moderated to a range potentially suitable for liquid water and Earth-like biochemistry. Initial mapping identified what appeared to be vast shallow seas within parts of this zone, supporting earlier spectroscopic evidence of surface water. Cloud patterns suggested an active hydrological cycle, with moisture evaporating from the hot day side and precipitating in the cooler regions near the terminator. The orbital insertion maneuver, executed in June 2280, represented the culmination of a century of precise navigation. The main engines fired in a carefully calibrated burn that placed Pioneer 1 in a stable orbit around Proxima Centauri, approximately 120 million kilometers from the star, positioned to facilitate detailed observation of all 5 planets in the system while maintaining safe distance from stellar flare activity. From this position, the ship deployed its full array of remote sensing technologies to study Proxima b. Detailed spectroscopic analysis confirmed an atmosphere composed primarily of nitrogen, 68%, and oxygen, 26%, with water vapor, carbon dioxide, and trace gases making up the remainder. Surface pressure measurements indicated conditions similar to Earth at moderate elevations, about 80% of Earth's sea level pressure. Most exciting were the strong biosignature indicators. Seasonal variations in atmospheric composition showed patterns consistent with widespread photosynthetic activity. Reflection spectra from the surface revealed absorption bands characteristic of chlorophyll-like pigments, particularly in the habitable terminator regions. While not absolute proof of life, these findings presented compelling evidence that Proxima b hosted at least simple photosynthetic organisms, potentially the first confirmation of life beyond Earth. The question of landing site selection dominated scientific discussions aboard Pioneer 1 during 2281. The terminator zone offered the most Earth-like conditions, but its precise characteristics varied significantly along its circumference. Some regions showed evidence of shallow seas with island archipelagos, while others appeared to be vast plains with possible river systems. The persistent hurricane-like storm systems, where atmospheric flows from day and night sides collided, complicated the analysis, creating regions of potential hazard. After months of debate and intensive observation, consensus formed around a region nicknamed Haven Peninsula, a landmass extending from the night side into the terminator zone, bordering a shallow sea. This location offered several advantages: moderate temperatures, proximity to water resources, protection from the most intense storm systems, and strong biosignature readings suggesting potentially fertile soils. The mission plan called for extensive robotic exploration before any human landing. Throughout 2282, Pioneer 1 constructed and deployed a series of autonomous probes designed to investigate Proxima b's surface conditions. These ranged from atmospheric drones to collect air samples, and map weather patterns to surface rovers equipped to analyze soil composition, radiation levels, and potential biological material. The first surface probe touched down on Proxima b in March 2283, landing on Haven Peninsula approximately 20 kilometers from the selected primary settlement zone. Its cameras transmitted the first images from the surface of a potentially habitable exoplanet, a moment many historians consider among the most significant in human history. The landscape revealed by these images appeared simultaneously alien and familiar. Under the deep red-tinged light of Proxima Centauri, the terrain showed geological features recognizable to terrestrial eyes: hills, valleys, and what appeared to be dried river channels. The sky displayed a perpetual twilight gradient, deepening to near black toward the night side, while brightening to a rich crimson toward the day hemisphere. Most remarkable were the surface organisms visible even in the first images. Carpet-like growths covered substantial portions of the rocky terrain, displaying colors ranging from deep purple to black, adaptations to maximize energy absorption from Proxima Centauri's red-weighted light spectrum. Near water sources, these gave way to more complex structures resembling Earth's primitive algal mats, but organized in concentric patterns oriented toward the distant sun. Subsequent probes confirmed what the first images suggested. Proxima b hosted a biosphere, albeit one less complex than Earth's. No evidence of animal-like multicellular organisms was discovered, but the planet supported a diverse ecosystem of photosynthetic and chemosynthetic life forms comparable to Earth's Precambrian era. This discovery, the first confirmed extraterrestrial biosphere, represented a scientific breakthrough of incalculable significance. The question of potential contamination, both of Earth organisms affecting Proxima b and local life forms posing risks to humans, received careful consideration. Extensive testing found the biochemistry of local organisms to be based on familiar building blocks, carbon compounds, amino acids, and nucleic acid analogs, but with significant structural differences from terrestrial biology. These differences suggested minimal risk of cross-infection or competition, though strict protocols were established to prevent unintended biological exchange in either direction. With surface conditions confirmed habitable and contamination risks assessed as manageable, preparation began for the first human landing. The journey from Pioneer 1's orbit to the surface would use specialized descent craft designed for Proxima b's conditions. These vehicles, constructed in the ship's manufacturing facilities using materials carried from Earth or produced during the journey, underwent rigorous testing throughout 2284. On April 12, 2285, chosen to honor the anniversary of Yuri Gagarin's first human spaceflight 324 years earlier, the landing craft Earthrise departed Pioneer 1 with a crew of 12. The descent through Proxima b's atmosphere took approximately 3 hours, with the craft executing a series of spiral maneuvers to minimize heating while collecting atmospheric data at multiple elevations. The landing itself, on a flat plain within Haven Peninsula, proceeded exactly as planned. Contact with the surface was confirmed at 14:37 ship time, followed by system checks and careful monitoring of external conditions before the hatch opening sequence began. At 15:22, the first human set foot on a world orbiting another star, a moment transmitted back to Pioneer 1 and recorded for eventual reception on Earth, though the transmission would take over 4 years to reach our solar system. The words spoken at that moment, chosen through consultations involving the entire ship community, acknowledged both the culmination of the century-long journey and the beginning of humanity's interstellar expansion. From Earth to the stars, we carry the light of human consciousness to new shores. May our presence here honor all who made this journey possible and benefit all who will follow. The initial surface expedition lasted 14 days, during which the 12-person team established a preliminary research station and conducted extensive surveys of the surrounding region. Portable laboratory equipment confirmed the initial probe findings regarding local biology, while identifying additional organisms in soil and water samples. Geological assessments established the mineral resources available in the region, focusing on materials that would support expanded human presence. Following this successful initial landing, a phased establishment plan began implementation. A series of modular habitat structures, manufactured aboard Pioneer 1 and transported to the surface, formed the core of what would become Promethean Base, humanity's first permanent settlement on an exoplanet. By the end of 2287, a continuous human presence had been established on the surface, with rotating crews of 20 to 30 personnel conducting research and developing infrastructure. The most ambitious engineering project of this early period was the Environmental Adaptation Dome, a pressurized structure 200 meters in diameter, where conditions were carefully managed to support Earth organisms, including agricultural plants. This controlled environment allowed for food production independent of ship supplies, while providing a testing ground for potential future ecosystem interactions. The dome also served as a psychological support for the surface crews, offering a space where they could experience something closer to Earth conditions, complete with simulated 24-hour day cycles and familiar flora. Throughout these developments, Pioneer 1 remained humanity's primary habitat in the Alpha Centauri system. The majority of the ship community continued to live aboard the vessel, now established in a stable orbit that optimized communication with both the surface base and Earth. From this position, the ship coordinated exploration of the wider Alpha Centauri system, dispatching automated probes to study the other planets in greater detail, and maintaining comprehensive monitoring of Proxima Centauri's stellar activity. Communication with Earth represented a bittersweet aspect of the mission's success. By 2290, transmissions detailing the landing and initial settlement of Proxima b had reached our solar system, allowing humanity's home civilization to share in the achievement. The responses from Earth, arriving after the nearly 9-year round-trip communication delay, expressed collective pride and wonder at what their interstellar emissaries had accomplished. Yet this communication also highlighted the tremendous separation between the two branches of humanity. Pioneer 1's community now numbered over 200, including more than 30 individuals born during the mission who had never known Earth directly. For them, and increasingly for the original Earth-born crew as well, their identity centered on their role in establishing humanity's presence in the Alpha Centauri system, rather than maintaining connections with a home world they would never see again. This evolving identity found expression in the Centaurian Charter, drafted in 2292 to establish governance principles for human presence in the Alpha Centauri system. While acknowledging origins and ongoing kinship with Earth, the Charter asserted the autonomy of the Centaurian community and established frameworks for decision-making regarding resource utilization, expansion planning, and potential contact with indigenous life forms. The philosophical impact of becoming a multi-star species manifested in cultural and artistic expressions throughout the community. The second Genesis movement celebrated the opportunity to define human existence in a new context, free from many of Earth's historical burdens while learning from its mistakes. Visual arts increasingly incorporated the distinctive light quality of Proxima Centauri and the unique landscapes of its habitable world, while music explored rhythmic patterns inspired by local phenomena such as the atmospheric cycles at the Terminator line. By 2295, planning had begun for expanded human presence within the Alpha Centauri system. Long-range surveys identified resource-rich asteroids that could support manufacturing and construction without depleting Proxima B's environment. Preliminary designs were developed for an orbital habitat around Alpha Centauri A, taking advantage of the more sun-like star's energy output and potentially allowing for less engineered living conditions than those required near Proxima Centauri. The Constellation program, formalized in 2297, outlined a 200-year vision for human development throughout the system. This ambitious plan envisioned a network of habitats, research stations, and eventually settlements leveraging the diverse environments offered by the three stars and their planetary systems. The program embodied the community's growing confidence in their ability to thrive in their new stellar neighborhood and potentially expand human presence beyond even Alpha Centauri in future generations. As the 24th century approached, the human presence in Alpha Centauri had firmly established itself as viable and growing. Promethean Base had expanded to accommodate up to 100 personnel, with plans approved for a second surface settlement on another region of Proxima B. Pioneer 1 continued its dual role as primary habitat and mission coordination center, while plans progressed for additional spacecraft constructed from in-system resources. The scientific returns from this unprecedented interstellar presence proved even richer than anticipated. Studies of Proxima B's simple biosphere offered profound insights into convergent and divergent evolutionary pathways, suggesting certain aspects of carbon-based life might be universal, while others were contingent on specific planetary conditions. The detailed observations of 3 different stellar types within one system revolutionized astrophysical models of star formation and evolution. Even the human biological and psychological studies, documenting adaptation to a new stellar environment, provided unique data impossible to obtain elsewhere. Perhaps most significantly, the Alpha Centauri mission demonstrated that interstellar travel, while enormously challenging, lay within humanity's capability. The technologies, methodologies, and social structures developed for Pioneer 1 provided a template that could potentially be refined and replicated for journeys to other nearby stars. What had once seemed an impossible dream, human expansion beyond our solar system, had become established reality. As 2300 arrived, marking 150 years since Pioneer 1's departure from Earth, the mission held a sesquicentennial commemoration connecting all elements of the human presence in Alpha Centauri. From the ship in orbit to the surface settlements, from research outposts to the construction facilities developing infrastructure for future expansion, the community gathered virtually to reflect on their journey and look toward the future. The ceremony concluded with the dedication of the Bridge Monument at Promethean Base, a sculpture incorporating materials from Earth, elements from Pioneer 1, and local materials from Proxima B. This symbolic bridge between worlds represented not merely the distance traversed, but the enduring connection between humanity's birthplace and its new frontier among the stars. In the warm red light of Proxima Centauri, beneath skies never before witnessed by human eyes, our species had established its first foothold around another sun. The distance between these new settlers and their ancestral home, measured not just in light years, but in generational and cultural terms, could not diminish the significance of what they had achieved. Humanity had become an interstellar species, fulfilling an aspiration as old as our first glances toward the night sky. The journey to Alpha Centauri, conceived in the hopeful imagination of early 21st century visionaries, had transformed from theoretical possibility to living reality. The path from Earth to the stars, once viewed as impossibly distant, had been traveled by human minds, bodies, and the shared aspirations of a species unwilling to remain bound to a single world or illuminated by a single sun. As Pioneer 1's crew and their descendants looked up from their new home at the distinctive patterns of an alien sky, they embodied the culmination of humanity's oldest dream and the beginning of its newest chapter, a presence no longer limited to our native solar system, but extending outward to embrace the wider cosmos that had always beckoned us onward.